Jupiter is the largest planet in our solar system. It is so big that more than 1,000 Earths could fit inside it. It seems like it is right there when we look at the sky, but the truth is very different. When scientists calculated how long it would take us to get there, the result changed everything we thought about space travel. With the technology we have today, a spacecraft would need many years just to get close to this gas giant. This made researchers ask something important. Will humans ever be able to set foot on Jupiter's moons? Get ready to fall asleep while you listen to this video and discover the secrets of this incredible journey through space. Subscribe to the channel, leave your like and comment where in the world you're watching from. Get comfortable and relax. Let's begin. You look up at the night sky and there it is, Jupiter, seemingly a bright, steady star, feeling almost close enough to touch. That feeling is a beautiful illusion because the reality of getting there involves crossing a gulf of space so vast it redefines our understanding of distance. Let's talk about that gap, because the very first thing you need to wrap your head around when planning a trip to Jupiter is that there is no single answer to the question of how far away it is. We are not sitting still on a cosmic map with fixed roads. The solar system is a fluid, swirling dance of orbits, and the distance between any two planets is a constantly shifting number. Think of it like two runners on separate tracks around a central field. Sometimes they're on the same side, feeling close, and other times they're on opposite sides, at their maximum separation. For Earth and Jupiter, this difference is not trivial. It is the difference between an already unimaginable journey and an even more unimaginable one. At our closest possible approach, when Jupiter is in a position astronomers call opposition, the distance shrinks to about 365 million miles. That is the best case scenario, but wait for the orbits to carry us to opposite sides of the Sun, and that distance balloons to over 600 million miles. We are talking about a variance of well over 200 million miles depending on when you leave. Those numbers are just too big to feel. Let's try to scale it down. Imagine the distance from the Earth to the Moon, 250,000 miles, a journey that took Apollo astronauts 3 days. Now picture stacking that distance up, not dozens, not hundreds, but thousands of times. The shortest trip to Jupiter is like making 1,500 of those Earth-Moon journeys back to back. The longest is more than 2,400. That is the playing field. This is why astronomers don't even use miles or kilometers when talking shop within the solar system. The numbers become ungainly. They use a measuring stick called the astronomical unit, or AU. 1 AU is defined as the average distance from the Earth to the Sun, about 93 million miles. It is the fundamental block of inner solar system real estate. Jupiter, being the giant of our neighbourhood, orbits much farther out. Its path is not a perfect circle, so its distance from the Sun varies from about 4.2 AU to 6.2 AU. Since Earth is at 1 AU, you can start to see the geometry. The closest Jupiter ever gets to us is when it is at its closest to the Sun, and we are at the point in our orbit farthest from the Sun, but on the same side. That minimum distance is roughly 4.2 AU. The farthest is when Jupiter is at its aphelion, farthest from the Sun, and we are on the opposite side of our orbit. That distance can stretch to over 6.2 AU. So, your spacecraft is not just aiming at a planet, it is aiming at a moving target that is itself travelling at tens of thousands of miles per hour along a curved path hundreds of millions of miles away. You cannot point a rocket at where Jupiter is in the sky tonight and fire. If you did, by the time you got there, Jupiter would be long gone, having completed a significant portion of its 12-year orbit around the Sun. This is the first and most fundamental concept in planning any interplanetary mission: trajectory. You must aim for where Jupiter asterisk will be asterisk months or years in the future, launching your spacecraft onto a long, arcing path that will intersect with Jupiter's own orbit at precisely the right moment. This is also why the timing of your launch is everything. Miss your specific launch window, a period of several weeks when the planetary alignment is just right, and you might have to wait over a year for the next opportunity, because that is how long it takes for Earth and Jupiter to return to a similar relative position. This celestial choreography means the journey is never a straight line. The most energy-efficient route, the one that requires the least amount of rocket fuel, is called a Hohmann transfer orbit. Picture this. You give your spacecraft just enough of a boost to push its orbit from a small, Earth-like circle around the Sun into a much larger elliptical path. This new orbit's far end, its aphelion, is designed to just touch the orbit of Jupiter. The spacecraft then coasts, unpowered, for the vast majority of the trip, slowly climbing away from the Sun's gravity, getting slower and slower until it reaches that highest point. If the timing is perfect, Jupiter arrives at that exact same point in space at the exact same time. This method is elegant and fuel cheap, but it is not fast. A Hohmann transfer to Jupiter takes roughly 5 to 7 years depending on the specific alignment. That is half a decade of silent coasting through the interplanetary void. But what if you want to get there faster? You can, but physics demands a steep price. A faster trajectory means a more direct route, a tighter ellipse that requires your spacecraft to be going much, much faster at the outset. To achieve that speed, you need a more powerful rocket or a series of complicated gravitational slingshots, which we will discuss later. Or you must carry an enormous amount of fuel to fire your engines for longer. There is a brutal equation in rocketry called the Tsiolkovsky rocket equation that governs this trade-off. In simple terms, to increase your final speed by a little, you need to carry exponentially more fuel, and that fuel itself has mass, requiring even more fuel to push it. This is often called the tyranny of the rocket equation. So, for a robotic mission, where you have a patient team of scientists on Earth and a spacecraft that can be put into hibernation, the long, slow, fuel-efficient Hohmann transfer is often the chosen path. It allows you to carry more scientific instruments instead of fuel. For a hypothetical human mission, where you want to minimize the radiation exposure and psychological strain on a crew, you would desperately want a faster transit. But the fuel requirements become absolutely astronomical, likely impossible with current chemical rocket technology. This is the core dilemma shaped by that initial illusory distance. Now, let's ground this in some real-world examples to see how these principles play out. History gives us a perfect spectrum of travel times to Jupiter, each telling a story about the technology and goals of its era. The first spacecraft to ever make the journey was Pioneer 10, launched in March 1972. It took a relatively direct, high-energy trajectory and reached Jupiter in just under 1 year and 9 months, flying by in December 1973. That is remarkably fast. Why so quick? Because its mission was a pioneering flyby. It did not need to slow down to orbit Jupiter. It just needed to get there, take pictures and data as it screamed past, and continue on its way. It was a bullet shot across the solar system. The Voyager probes, launched 5 years later, also benefited from a rare grand alignment of the outer planets. Voyager 1, using a more powerful launch vehicle and a perfect trajectory that included a gravity's assist from Jupiter itself to fling it onward to Saturn, made the journey in only 1 year and 6 months, arriving in March 1979, even faster than Pioneer. Then consider the Galileo mission, which was designed to do something much harder. Not just fly by it, but actually go into orbit around Jupiter to study it and its moons for years. To carry enough fuel to slow down and be captured by Jupiter's gravity, it had to take a much longer, more circuitous route. Launched in October 1989, it used gravity assists from Venus once and Earth twice in a complex planetary billiard shot to gain enough momentum. It finally arrived at Jupiter in December 1995, a total travel time of over 6 years. The trade-off was clear, a longer journey for a much richer, longer-lasting scientific payoff. More recently, the New Horizons mission, designed for pure speed to get to Pluto, passed by Jupiter for a gravity assist in February 2007, just 13 months after its launch. It holds the current speed record for a Jupiter arrival. And finally, Juno, which went into orbit around Jupiter's poles in July 2016, took almost 5 years, using a trajectory that avoided the worst of Jupiter's radiation belts during its approach. So, as you can see, the answer to how long does it take ranges from 1 year and 1 month to over 6 years. It all depends on what you want to do when you get there, how much money and fuel you have for your rocket, and the precise celestial mechanics of your launch date. This immense variable distance also creates other profound challenges beyond just travel time. Communication becomes an exercise in patience. When Juno is at Jupiter, over 480 million miles away, radio signals travelling at the universal speed limit, the speed of light, take over 43 minutes to make the one-way trip. That means if you send a command to the spacecraft, You wait 86 minutes just to see if it was received and executed correctly. This forces spacecraft to be incredibly autonomous, able to diagnose problems and perform critical maneuvers on their own. For a future human crew, this communication delay would mean total independence from mission control. A conversation with Earth would have pauses of nearly an hour and a half between sentences. The distance also means power is a challenge. Solar power, so abundant near Earth, dwindles to less than 1/25th of its strength at Jupiter's orbit. That is why missions like Juno use huge solar panels, the size of truck trailers, just to generate enough electricity to run its instruments, or why other outer planets' missions rely on nuclear thermal generators. The sheer scale of the distance influences every single aspect of the mission design, from the thickness of the wiring to the type of computer memory used. So, the next time you see that bright spot in the sky, remember the illusion. The beauty of Jupiter shining in our night sky belies the incredible, dynamic, and daunting gulf that separates our world from that gas giant. Crossing that gulf is the greatest engineering challenge humanity has ever undertaken, a testament to our understanding of physics and our desire to explore. The journey is not a simple leap. It is a meticulously calculated, years-long cosmic rendezvous, where distance is not just a number, but the defining constraint of the mission itself. It is a humbling reminder of our place in a solar system that is overwhelmingly vast, and a brilliant showcase of how we have learned to navigate that vastness. We do not fly in straight lines, we surf the gravitational contours of the sun and planets, turning the solar system into a network of interplanetary highways. That bright point of light is a destination that demands not just courage, but an immense amount of patience and precision. It represents a frontier that remains, despite our robotic ambassadors, profoundly distant. Reaching it within any reasonable time frame requires us to work asterisk with asterisk, the fundamental laws of orbital mechanics, not against them. We use the motion of the planets themselves as catapults and guides. This is the elegant, complex reality behind that simple, beautiful sight. The distance is both a barrier and a teacher, forcing us to develop smarter, more efficient ways to travel. Every mission that makes the journey adds to our collective knowledge, not just about Jupiter, but about how to traverse the spaces between worlds. It is a slow, step-by-step process of extending our reach. And while the distances are mind-bending, the fact that we can calculate these journeys down to the second and successfully complete them is one of the most remarkable achievements of our species. We have transformed the abstract mathematics of celestial motion into practical roadmaps across millions of miles. So, the time it takes is more than a statistic. It is a reflection of our current technological capabilities, our budgetary constraints, and our scientific ambition. As we develop new propulsion technologies, that time may shrink. But for now, travelling to Jupiter means committing to a timescale of years, a project that will outlast presidential administrations and personal milestones. It is a long-term investment in discovery, a physical manifestation of human curiosity slowly, patiently crossing the cosmic ocean to touch another world. So we have established that the journey to Jupiter is a matter of navigating immense and dynamic distances, a patient celestial rendezvous. But what actually pushes a spacecraft across that gulf? The answer is the engine, and the type of engine you use is the single most important factor deciding whether your trip takes 13 months or 13 years. This is the core technological bottleneck, the great limiter of interplanetary travel. It is not just about distance, it is about how you overcome inertia to change your velocity, a concept rocket scientists call delta V. Every gram of a spacecraft, from its cameras to its computer chips, must be accelerated away from Earth's powerful gravity and then guided onto a precise path toward Jupiter. The method you choose to provide that push defines everything about the mission's timeline, cost, and even its scientific goals. Let us start with what most people picture when they think of space travel, the chemical rocket. This is the technology that took humans to the moon and launches every satellite today. Its principle is straightforward and violent. Mix a fuel and an oxidizer, ignite them, and direct the explosive hot gases out of a nozzle. The reaction pushes the rocket in the opposite direction. The key advantage here is raw power. Chemical engines generate a tremendous amount of thrust, a big, muscular shove that is absolutely necessary to break free of Earth's gravity well in a matter of minutes. Think of the dramatic, fiery liftoff of a Saturn V or a Falcon Heavy. That is chemical propulsion at work. But this brute force approach has a critical downside. It is incredibly inefficient in the long run. The engine burns through its entire tank of propellant in a very short time, often just a few minutes. Once that fuel is spent, the rocket's job is mostly done. The upper stage, now carrying the spacecraft, gives one or two final, shorter burns to set it on the correct trajectory, and then nothing. For the vast majority of the multi-year journey to Jupiter, the spacecraft is simply coasting, a silent, unpowered projectile gliding along the curved path set by the sun's gravity. It cannot speed up and it cannot slow down until perhaps the very end, when it might fire small thrusters for a course correction or a major engine burn to enter orbit. This coasting phase is why minimum energy trajectories like the Hohmann transfer take so long. You're riding the slowest possible rail to your destination because your initial fuel supply was so quickly exhausted. Chemical rockets are like a sprinter who explodes out of the blocks with incredible speed but then has to jog the rest of the marathon. They're great for the initial kick, but terrible for sustained speed across interplanetary space. This limitation is why engineers have developed and are perfecting a completely different class of engines: electric propulsion, most notably ion thrusters. You might have seen science fiction movies with ships that glow with a faint blue light that is based on real technology. An ion engine works by using electricity, usually from solar panels, to strip electrons off atoms of a noble gas like xenon, creating positively charged ions. These ions are then accelerated out of the back of the engine using powerful electric fields. The key difference is the exhaust velocity. The ions are shot out at speeds up to 10 times faster than the exhaust from a chemical rocket. This makes the engine much more efficient, meaning it gets a lot more push from the same amount of propellant mass. However, there is a trade-off. The thrust from an ion engine is minuscule, often compared to the force of a single piece of paper resting on your hand. It cannot possibly lift a spacecraft from Earth's surface. But in the frictionless vacuum of space, where there is no air resistance, that tiny continuous force adds up. An ion engine can fire for weeks, months, or even years, slowly and steadily accelerating the spacecraft to tremendous speeds over time. This is the tortoise to the chemical rocket's hare. A mission using ion propulsion would start its interplanetary journey with a chemical rocket kick. But then, once in orbit, it would deploy its solar arrays and turn on its ion drive for the long haul. It would not follow a slow elliptical Hohmann transfer orbit. Instead, it could take a more direct, spiralling path, constantly accelerating for a large portion of the voyage, then flipping around and decelerating for the arrival. While this might not always be faster for a destination as far as Jupiter with current solar panel limitations, for many missions it offers a better balance of speed and payload. The Dawn spacecraft, which visited the asteroids Vesta and Ceres, used ion propulsion to become the first mission to orbit 2 extraterrestrial bodies, something impossible with a chemical propulsion system on that budget. For Jupiter, the weak sunlight makes large solar panels challenging, but not impossible, as Juno proved. More advanced electric propulsion concepts, like Hall effect thrusters or magnetoplasmodynamic thrusters, offer variations on this theme of high efficiency and low, continuous thrust. The promise of these systems is a future where we can carry more scientific instruments and less fuel, or choose faster trajectories without the exponential fuel penalty of chemical rockets. But the real game changers, the technologies that could slash travel times to Jupiter to under 2 years, lie further on the horizon. One of the most promising and actively researched is nuclear thermal propulsion. Imagine replacing the chemical combustion chamber of a rocket with a compact nuclear reactor. Instead of burning fuel, you use the reactor's heat to blast a propellant like liquid hydrogen through a nozzle. The hydrogen, heated to extreme temperatures, flies out at much higher speeds than chemical exhaust, effectively doubling or tripling the engine's efficiency. This means you could generate thrust levels comparable to chemical rockets, but for much longer durations because you are carrying a lightweight propellant and a separate energy source, the reactor. A spacecraft with a nuclear thermal engine could perform a powerful burn to leave Earth orbit, then another sustained burn midway to adjust its path, and finally a major burn to slow down at Jupiter. This would enable much faster transfer orbits, cutting travel time dramatically. Studies have shown that with robust nuclear thermal propulsion, a crewed mission to Mars could be months instead of nearly a year, and a robotic mission to Jupiter could be accomplished in roughly 2 to 3 years. The technology was ground tested here on Earth decades ago, but never flown. Today there are serious initiatives to develop and demonstrate flight-ready nuclear thermal propulsion systems for cislunar space and beyond. A step beyond that is nuclear electric propulsion. Here, a nuclear reactor, either fission or someday fusion, is used not to heat propellant directly, but to generate massive amounts of electricity. That electricity then powers extremely powerful versions of ion or plasma thrusters. This combines the high energy density of nuclear power with the superb efficiency of electric propulsion. A spacecraft with a nuclear electric drive could thrust continuously for years, building up speeds that are simply unthinkable with today's technology. It would be the ultimate interplanetary cruiser, capable of fast transits to the outer planets while still retaining the ability to slow down and orbit upon arrival. The challenge is engineering a compact, reliable and safe space-rated nuclear reactor and managing the waste heat it generates. Then there are the more visionary concepts, like the solar sail. This is propulsion without any propellant at all. The solar sail is a gigantic, ultra-thin, reflective sheet that uses the tiny but constant pressure of sunlight for thrust. Photons from the sun bounce off the sail, imparting momentum. The push is incredibly faint, weaker even than an ion engine, but it is free and endless. Within the inner solar system, solar sails can perform remarkable maneuvers. For a journey to the outer planets, however, where sunlight grows weak, the acceleration would be very slow. The solution might be laser sailing, where giant Earth or orbit-based lasers beam energy onto the sail, providing a powerful push even far from the sun. This is firmly in the realm of theoretical engineering, but it points to a future where we might propel lightweight probes at a significant fraction of the speed of light to other stars. For Jupiter missions in the nearer term, the more likely candidates are nuclear thermal or advanced electric propulsion. Each of these technologies redefines the trade-offs. With chemical rockets, the mission designer is forced to choose between a fast, fuel-guzzling trajectory or a slow, economical one. With advanced propulsion, that dichotomy softens. You can begin to contemplate direct trajectories that are both faster and more flexible, missing the strict launch windows that govern chemical rocket missions. This would make the solar system feel much more accessible. You could launch a mission to Jupiter almost any time, not just once every 13 months. The development of these systems is driven by the desire to overcome the time barrier, not just for robots, but for humans. As discussed, sending people to Jupiter is a monumental challenge, and the multi-year cruise duration of a chemically propelled ship is likely a showstopper due to radiation supply needs and psychology. A nuclear thermal rocket that can cut that transit to under 2 years makes the idea, while still colossal, at least conceivable for future generations. So, when you look at the historical travel times of our Jupiter missions, from Pioneer's 1 year and 9 months to Galileo's 6 years, you're not just looking at different trajectory choices, you're looking at the evolution of propulsion technology and the mission priorities of their eras. Pioneer and Voyager were fast flybys enabled by powerful chemical upper stages and favourable alignments. Galileo needed to carry enough fuel to slow down, so it used a slow, gravity-assisted path. New Horizons was a bullet shot with the most powerful chemical launcher available at the time. Juno used a large chemical rocket, but a trajectory that balanced radiation safety and arrival time. The next generation of Jupiter orbiters or moonlanders might very well be equipped with high-power electric thrusters, allowing them to carry more instruments or arrive sooner. In the end, the engine is the heart of the mission. It is the technology that translates our blueprints and calculations into motion. The distance to Jupiter is a fixed law of orbital mechanics, but the time it takes to cross it is a variable of our engineering ingenuity. The development of propulsion is a slow, incremental, and often underappreciated field, but it is the absolute key to unlocking the solar system. While we marvel at the stunning images sent back by our distant spacecraft, it is worth remembering the silent, patient, or powerful push that got them there. That push, whether a brief, fiery explosion or a years-long faint blue glow, is the physical manifestation of our desire to explore. As we invest in the next leap in propulsion technology, we are not just building better engines, we're shrinking the effective size of our solar system, turning journeys that once took a generation of mission controller's career into routine expeditions. The clock on a trip to Jupiter is counting down, not because the planets are moving closer, but because we are learning how to move faster. So we have the engine technology, the power to push, but raw power is useless without a plan. roadmap through the moving maze of the solar system. You do not just point your advanced rocket at Jupiter and fire. That would be like trying to shoot a speeding bullet with another bullet from 1,000 miles away while both of you are on separate merry-go-rounds. The actual path the spacecraft takes is a masterpiece of prediction and patience, a slow celestial dance where timing is absolutely everything. This dance is governed by the immutable laws of orbital mechanics, and understanding it is the key to unlocking not just Jupiter, but the entire solar system. Think of it this way. Every object in the solar system, from the Sun to the smallest asteroid, is in constant curved motion held in place by gravity. To travel from one to another, you must make your spacecraft's orbit around the Sun change to intersect with your target's orbit. The most famous and fundamental of these interplanetary highways is called the Hohmann transfer orbit, named after the German scientist who calculated it. Imagine two circles, one representing Earth's orbit and a larger one representing Jupiter's orbit. The most fuel-efficient way to travel between them is not a straight line, but an elliptical path that just touches both circles. You give your spacecraft one carefully calculated push at just the right point in Earth's orbit. This boost widens its path from a near circle into a long, skinny ellipse. The spacecraft then spends months or years coasting along this new ellipse, climbing slowly away from the Sun, slowing down as it fights solar gravity, until it reaches the farthest point, the aphelion. If you timed everything perfectly, Jupiter arrives at that exact same point in space at the exact same moment. This is the celestial handshake, the minimum energy rendezvous. It is the interplanetary equivalent of coasting downhill. You use the least amount of rocket fuel possible, but efficiency has a cost: time. A Hohmann transfer orbit to Jupiter is a long, slow arc. Depending on the specific alignment, it typically takes between 5 and 7 years. That is half a decade of silent cruising. This is why launch windows are so critical. You cannot launch on a Hohmann transfer whenever you want. The planets must be in the correct relative position at the start so that they will both be at the right points at the end. For Earth and Jupiter, this specific geometric alignment, where Jupiter is about 55 to 60 degrees ahead of Earth in its orbit at the time of launch, repeats roughly every 13 months. This is your launch window. It is a period of several weeks, sometimes just a single day, when the celestial geometry allows for this efficient transfer. Miss that window, and you have two choices: wait for the next one over a year later, or spend a prohibitive amount of fuel trying to force a faster, less efficient trajectory. This 13-month cycle is the heartbeat of missions to the outer planets. Mission planners live and breathe these calendars, scheduling years of work around these brief opportunities. But what if you do not want to wait 5 to 7 years? What if your science demands a faster arrival, or your spacecraft is a flyby that does not need to carry extra fuel for slowing down? Then you leave the efficient Hohmann highway and take a more direct, higher energy route. This is like taking a steeper, more direct road up a mountain instead of the long, winding switchbacks. It gets you there faster, but it requires a lot more energy up front. In practical terms, this means your rocket must impart a much greater initial speed to the spacecraft. Instead of just nudging it onto that long ellipse, you shove it hard, putting it on a tighter, faster curve that cuts across the solar system more directly. The New Horizons mission to Pluto is the classic example of this. It used a powerful Atlas V rocket with additional solid rocket boosters to achieve one of the fastest speeds ever for a departing spacecraft. It passed Jupiter's orbit in just 13 months, not 5 years. The trade-off is brutal, however. To achieve that higher speed, you need a much larger rocket or a much lighter spacecraft, often both. The tyranny of the rocket equation rears its head. The fuel required for that extra speed does not increase linearly, it increases exponentially. This is why fast missions are rare and expensive. They often carry smaller payloads of scientific instruments, because every gram of camera or spectrometer is a gram that could have been fuel for a faster trip. So the trajectory becomes a central part of the mission's identity. Is it a patient, heavy orbiter like Galileo taking 6 years but carrying a full suite of instruments and the fuel to slow down? Or is it a speedy flyby like New Horizons, a lightweight bullet packed with essential sensors but screaming past its target with no chance to stay? The choice is dictated by the science goals and the budget. There is another layer of complexity too. Gravity assists. While not the primary focus of this particular celestial dance, they are an inseparable part of the choreography. Sometimes, the most efficient path to Jupiter is not direct, but involves swinging by another planet first, like Venus or Earth itself, to get a gravitational kick that slingshots the spacecraft outward. This can actually save fuel compared to a direct Hohmann transfer, though it often adds time to the overall journey as the spacecraft takes a detour. The Galileo mission used this technique masterfully, swinging by Venus once and Earth twice, to gain enough momentum to reach Jupiter, because its main rocket was not powerful enough to send it there directly. This made its journey longer, but possible with the launch vehicle available. So the trajectory is a puzzle with many solutions, each with its own balance of time, fuel and mass. The process of calculating these paths is a field called astrodynamics, and it is a blend of deep physics and high-stakes logistics. Engineers use sophisticated software to model the gravitational pull of every major body in the solar system, the thrust curves of their engines, and the desired arrival conditions. They run thousands of simulations, looking for the optimal path that meets all the mission constraints. A tiny error in the initial burn can compound over millions of miles, causing the spacecraft to miss its target by a catastrophic margin. This is why mid-course corrections are planned. These are small, brief engine burns performed weeks or months into the flight to nudge the trajectory back onto the perfect course. They are the equivalent of a pilot making slight adjustments to the steering wheel on a long transoceanic flight. The precision involved is staggering. When the Voyager probes flew through the precision keyholes of the outer planet alignments, their navigation was so exact that they could thread the needle between moons and rings with error margins, measured in mere kilometres after journeys of billions of kilometres. This all circles back to the fundamental truth. In space travel, you're not driving a car on a static road. You're launching yourself onto a predetermined gravitational rail. Once you make that initial burn, your path is largely set by the laws of physics. You become a new artificial planetoid in orbit around the Sun, and your destiny is a matter of orbital geometry. This is why timing is everything. Launch a day late and you miss the optimal alignment. The required correction might demand more fuel than you have, or it might add years to the trip. This pressure creates the intense countdown to zero atmosphere of a planetary launch. It is not just about getting a rocket off the ground, it is about hitting a vanishingly small keyhole in both space and time. For a crewed mission, these constraints become even more severe. Asking humans to endure a 6-year coast to Jupiter is a much harder sell than for a robotic probe. Therefore, a human mission would almost certainly demand a higher energy, faster trajectory, requiring propulsion technology far beyond our current standard chemical rockets, as we discussed earlier. Nuclear thermal propulsion could provide the sustained thrust needed to follow a faster curve, making a 2 to 3 year transit conceivable. But even then, the principles of celestial mechanics remain. You would still have to plan your launch around a favourable window, calculate your transfer ellipse, and execute your burns with impeccable timing. The dance does not change, only the tempo increases. So when you see an animation of a spacecraft's path to Jupiter, that elegant swooping curve is not an artist's impression. It is the physical manifestation of celestial mechanics, a path carved by gravity and momentum. It is a road that only opens for business every 13 months, and once you're on it, there are no exits, no gas stations, and no U-turns. You are committed. This is the profound difference between exploring our planet and exploring our solar system. On Earth, you can stop, change your mind, or take a detour. On the way to Jupiter, you're riding a roller coaster designed by nature, and the only way off is at the end of the track. This incredible dependency on orbital dynamics also means that every mission is unique. The trajectory for the Juno mission was different from Galileo's, which was different from Cassini's to Saturn. Each was tailored to the spacecraft's capabilities, its scientific objectives, and the specific planetary alignment at its launch time. There is no one-size-fits-all route. This is the beautiful, challenging reality of interplanetary travel. It is a slow, patient, and precisely timed ballet, where we launch a piece of ourselves onto a path calculated years in advance, trusting physics to deliver it to a world that was just a speck of light in a telescope. It requires a kind of faith in mathematics and engineering, a belief that if we do our part correctly here on Earth, the universe will handle the rest, guiding our robotic ambassador along the invisible rails of gravity until, years later, it finally rings the doorbell of a giant. So the next time you hear about a launch to Jupiter, remember, They are not just launching a rocket, they are launching a calculation, a prediction of where Jupiter will be in half a decade, and betting everything on being right. We have talked about following the predetermined rails of orbital mechanics, a slow and patient dance with gravity. But what if you could cheat? What if you could steal a little bit of a planet's momentum to fling yourself across the solar system, like a cosmic thief getting a free ride? This is not science fiction. It is one of the smartest tricks in the book of space exploration, a fundamental technique that has made journeys to Jupiter and beyond possible. It is called the gravity assist, or the gravitational slingshot, and it is the secret sauce that turns the solar system into a network of interplanetary highways. The basic idea is beautifully simple, though the physics behind it can get intricate. Imagine you're on a swing. To go higher, you do not just sit there. You pump your legs at the right moment, adding a little bit of energy to the system each time. A gravity assist is like that, but instead of your legs, you're using the immense gravity and orbital speed of a planet. Here is how it works in practice. A spacecraft approaches a planet from behind, relative to the planet's direction of travel around the Sun. As it falls into the planet's gravitational well, it is pulled inward, accelerating. It swings around the planet in a curved path, like a stone whirled on a string, and is then flung out the other side. The critical part is that the planet itself is moving at a tremendous speed in its orbit. From the planet's perspective, the spacecraft simply comes in and leaves with the same speed. But from the Sun's perspective, the spacecraft has stolen a tiny, tiny fraction of the planet's orbital momentum. The planet, being astronomically massive, does not even notice the loss. It is like a speeding freight train not feeling a single snowflake that hits it. But for the spacecraft, that stolen momentum translates into a significant change in speed and direction. It is a free boost, no fuel required. Think of it like this. You're skating slowly across an ice rink. A much larger, faster skater comes up from behind, grabs your hand and swings you around, letting you go in front of them. You're now moving much faster, and the big skater has slowed down by an imperceptible amount. You've used their momentum to accelerate. That is the essence of a gravity assist. For missions to Jupiter, this technique is not just helpful, it is often essential. The most famous examples are the Voyager probes. Voyager 1 did not just fly to Jupiter, it used a precise encounter with Jupiter to get a massive boost that bent its path and hurled it onto Saturn. Then it used Saturn for another slingshot to fling it out of the solar system entirely. That initial Jupiter assist was the key that unlocked the outer solar system, but you can also use inner planets to help you get to Jupiter. The Galileo mission, which needed to carry a lot of fuel to slow down and orbit Jupiter, did not have a rocket powerful enough to send it there directly. So engineers designed a convoluted but brilliant path called the Vega trajectory, Venus-Earth-Earth gravity assist. Galileo launched toward Venus first. It flew by Venus to get a boost, then swung back by Earth for one assist, then by Earth again for a second final kick. Each planetary encounter pumped up its orbital energy, like a multi-stage pump on that swing, until it had enough momentum to climb all the way out to Jupiter. This path took 6 years, but it made the mission feasible with the available launch vehicle. Without those gravity assists, Galileo might never have left the drawing board. The New Horizons mission to Pluto also used a gravity assist from Jupiter, not because it needed the energy to get there, but because the boost cut its travel time to Pluto by years. It shot past Jupiter just 13 months after launch, and the planet's gravity bent its trajectory into a sharper curve toward the outer darkness, shaving about 3 years off the trip. So, the slingshot can be used for 2 main purposes: to change direction dramatically, as with Voyager, or to add pure speed, increasing the spacecraft's velocity relative to the Sun. The calculations for this are incredibly precise. You have to aim your spacecraft at a very specific point in space, a keyhole just a few hundred kilometers wide, years in advance. Hitting that keyhole ensures you will swing around the planet at the exact right altitude and angle to get the desired effect. Miss it, and you might get the wrong boost, or worse, crash into the planet or be flung off into a useless orbit. It is the ultimate example of precision driving, but there is a common misconception to clear up. A gravity assist does not mean you just fall toward the planet and get a speed boost for free in the sense of magic. The energy has to come from somewhere, and it comes from the planet's orbital motion. The spacecraft enters the planet's sphere of influence with a certain velocity and leaves with that same velocity asterisk relative to the planet asterisk. However, because the planet is moving around the Sun, the spacecraft's velocity relative to the Sun changes. If you approach the planet from behind, you leave with a higher solar orbital speed. If you approach head-on, you would actually lose speed relative to the Sun, which could be useful for slowing down to reach an inner planet like Mercury. For outer planet missions, you always want to approach from behind to gain speed. This technique completely changes the economics of space travel. By using gravity assists, you can launch a heavier spacecraft with a smaller, cheaper rocket, because you're not carrying all the fuel needed for a direct, high-energy transfer. You're trading fuel for time and clever navigation. That trade-off is why so many missions use it. The Cassini mission to Saturn used multiple assists from Venus, Earth and Jupiter. The Messenger mission to Mercury used assists from Earth, Venus and Mercury itself to slow down enough to enter orbit. It turns the planets into a giant interplanetary pinball machine, with our spacecraft as the ball. For a trip to Jupiter specifically, a gravity assist from Earth or Venus can be the first step in a longer journey. It might seem counterintuitive to fly inward toward Venus to eventually go outward to Jupiter, but it works. By first dropping closer to the Sun, a spacecraft can actually gain orbital energy more efficiently from a gravitational swing-by. It is like stepping backward to get a running start. This is the Vega trajectory in a nutshell. The spacecraft steals a little from Venus, then a little more from Earth, and even more from Earth again, each time pumping its orbit larger and larger until Jupiter's orbit is within reach. The downside, of course, is time. These detours add years to the cruise phase. But for a robotic mission, time is often the resource we have the most of, while fuel and launch mass are extremely limited. So, the gravity assist is the great enabler. It allows us to do more with less, to reach destinations that would otherwise be unreachable with current technology. It is a testament to human ingenuity, using the fundamental forces of nature as a tool. We are not just passively riding gravity's rails, we're actively manipulating our path by using the planets as gravitational gears. Looking to the future, gravity assists will remain a cornerstone of mission design, even as propulsion technology improves. For ultra-fast missions powered by advanced propulsion, a slingshot might provide that final, crucial bump to cut travel time further. For slower, more economical science missions, it will continue to be the primary method for reaching distant worlds without breaking the bank. It also introduces an element of beautiful complexity. Every mission becomes a unique puzzle, with engineers searching for the perfect combination of planetary alignments over a multi-year period to create a viable trajectory. They have to think years, sometimes decades ahead, plotting courses that will use planets as stepping stones. This long-term planning is a hallmark of deep space exploration. It requires patience and a vision that stretches far beyond political or funding cycles. When Galileo was executing its complex dance with Venus and Earth, it was following a plan laid down years before, a plan that relied on the predictable clockwork of the solar system. That reliability is what makes it all possible. The planets are always moving according to Newton's and Kepler's laws, and we can predict their positions centuries into the future with incredible accuracy. So, we can plan these intricate slingshot trajectories with confidence, knowing that if we launch our spacecraft at the right moment, Venus will be exactly where we need it to be years later to give it a push. This predictability turns the solar system from a vast, empty void into a structured, navigable space. The gravity assist is the technique that proves we are not just visitors in this system. We are beginning to learn how to move through it like natives, using the natural topography of gravity wells to our advantage. It transforms planets from mere destinations into tools, into launch pads and accelerators. So the next time you hear about a spacecraft arriving at Jupiter, remember, it might not have taken a direct route. Its journey was likely a grand tour, a pinball ride past other worlds, each one giving it a gentle or not so gentle nudge, building up the speed needed to reach the king of planets. That journey is a story of physics, precision, and patience, a story where we steal a ride from the cosmos itself to satisfy our endless curiosity. All that theory about trajectories and gravity assists is fascinating, but nothing makes it more real than looking at the actual clocks, the concrete timelines of spacecraft that have made the trip. History gives us the ultimate practical answer to the question of how long it takes to get to Jupiter. and the spread of those times tells a richer story than any single number ever could. Each mission was a product of its era's technology, its specific scientific goals, and the cleverness of its navigators. So let us walk through the real timeline of Jovian exploration, starting with the first Pioneer. In the early 1970s, the idea of sending a probe to the outer planets was still a monumental gamble. The mission was Pioneer 10, launched in March of 1972. Its goal was audacious yet simple: to be the first human-made object to pass through the asteroid belt and conduct a flyby of Jupiter. It did not have to slow down or enter orbit. It was a pathfinder, a scout. Engineers gave it a powerful push onto a direct high-energy trajectory. This was a brute force approach, using a strong chemical rocket to essentially shoot it like a bullet across the solar system. It survived the asteroid belt, a major worry at the time, and its cameras began to capture the first ever close-up images of the giant planet. Pioneer 10 reached Jupiter in December of 1973. The travel time, 1 year and 9 months. That is remarkably fast by any standard. It proved that a direct flight was possible, that the radiation belts, while fierce, could be survived, and it opened the door for more ambitious missions. Its twin, Pioneer 11, followed a year later on an even more clever path, using Jupiter's own gravity to sling it onto Saturn. But Pioneer 10's speedy journey set an initial benchmark. However, that benchmark did not last long. The very next visitors to Jupiter were the legendary Voyager probes, and they rewrote the rules. Launched in 1977, they benefited from a once-in-176 years alignment of the outer planets. Voyager 1, launched second but on a faster trajectory, had a singular clear goal: a detailed tour of Jupiter and Saturn with a focus on Saturn's moon Titan. To do this, it needed to get there efficiently. It used a near-perfect launch window and an optimized path that included a gravity assist from Jupiter itself to bend its trajectory towards Saturn. Voyager 1 made its closest approach to Jupiter in March of 1979. Its travel time? Just 1 year and 6 months, beating Pioneer 10's record. This was a combination of a powerful launch, excellent celestial mechanics, and the fact it too was a flyby with no need to slow down. Its images transformed Jupiter from a fuzzy disk into a dynamic, swirling world with intricate cloud bands and a raging storm larger than Earth. Voyager 2, on a slower grand tour trajectory that would take it to all 4 gas giants, arrived at Jupiter 4 months later, in July of 1979. But the next major mission had a completely different objective, and therefore a completely different timeline. That mission was Galileo. Launched in October of 1989 from the Space Shuttle Atlantis, Galileo was not a flyby. It was designed to do what no spacecraft had done before: enter orbit around Jupiter and release a probe into its atmosphere. This changed everything. To carry the fuel needed to slow down for orbital insertion and to accommodate the shuttle's launch constraints, Galileo could not take a direct, fast path. Instead, engineers designed that incredible Vega trajectory, Venus-Earth-Earth gravity assist. It flew by Venus in February of 1990, then by Earth in December of 1990 and again in December of 1992. Each flyby pumped up its orbital energy, like winding up a cosmic spring. Finally, on this long looping path it approached Jupiter. In July of 1995, it released its atmospheric probe, which dove into the clouds that December. The Galileo orbiter itself fired its main engine for a nail-biting 96 minutes, to break into orbit around Jupiter on the 7th of December 1995. Total travel time from launch to orbital insertion, just over 6 years. That is the trade-off in action. A fast flyby takes under 2 years, an orbiter with complex needs took 6. Galileo's journey was a masterclass in patient navigation and using the solar system's gravity to do the heavier lifting. Then, at the dawn of the new century, another fast traveller came along, though Jupiter was not its final stop. The New Horizons mission, launched in January of 2006 with the goal of reaching Pluto, was all about speed. It used the most powerful launch vehicle available at the time, an Atlas V with additional solid rocket boosters and a kick stage, to achieve the highest Earth escape velocity ever recorded. It was a lightweight, compact spacecraft built for a sprint. It passed the Moon's orbit in just under 9 hours, a journey that took Apollo astronauts 3 days. It screamed across the inner solar system and arrived at Jupiter for a gravity assist in February of 2007. Travel time from Earth to Jupiter, a mere 13 months. This is the current speed record for a Jupiter arrival. The assist from Jupiter not only bent its path toward Pluto, but also shaved about 3 years off its total travel time to the dwarf planet. New Horizons was a pure flyby, a gravitational leverage point, and it demonstrated how far launch vehicle technology had come since the Pioneer days. Following that, you have the most recent orbital visitor, Juno. Launched in August of 2011, Juno's goal was to orbit Jupiter's poles and study its interior, magnetosphere, and auroras. It used a large chemical rocket, but chose a trajectory that balanced several factors. Unlike Galileo, it did not use inner planet gravity assists. Instead, it performed a deep space maneuver in 2012, and then, in a surprising move, executed a flyby of Earth in October of 2013 for a final gravity assist to slingshot it out to Jupiter. But a key part of Juno's flight plan was managing the intense radiation around Jupiter. Its trajectory was designed to avoid the worst of the radiation belts during its initial approach and orbital insertion. This meant taking a wider, more cautious path. Juno fired its main engine to enter orbit around Jupiter on the 4th of July 2016. Its travel time, almost 5 years. So from 13 months to 6 years, the history of Jupiter missions shows a spectrum of travel times dictated by purpose. Pioneer 10 and Voyager 1 were fast flybys, pure reconnaissance missions. New Horizons was a high-speed passerby using Jupiter as a stepping stone. Galileo and Juno were orbiters, requiring more complex journeys to deliver a functioning, fuel-rich spacecraft to a point where it could successfully brake and stay. Each mission's timeline was a direct reflection of its engineering constraints and scientific ambition. What does this spread teach us? It shows that there is no single answer. If you ask how long it takes to get to Jupiter, you must ask a follow-up. To do what? To fly past at tens of thousands of miles per hour? That can be done in a year and a half or less. To go into orbit and study the system for years? That requires a 5 to 6 year cruise. The technology has not linearly decreased travel time. Instead, we have optimized for different objectives. We have learned to be faster when speed is the priority, and to be more patient and clever when the payload and orbital requirements are the priority. This historical record also sets expectations for future missions. The upcoming Europa Clipper mission, designed to study Jupiter's icy moon Europa in detail, is planned to launch in the next few years. It will not enter orbit around Europa directly due to the horrific radiation environment there. Instead, it will enter a wide orbit around Jupiter and make dozens of close flybys of Europa. Its trajectory is complex and may use gravity assists, and its estimated cruise time is about 5.5 years. It fits right into the historical pattern for a major, complex science mission to the Jovian system. So, when you imagine a future mission, you can look at this timeline. A simple flyby probe with a powerful new rocket might one day cut the time to under a year. A massive orbiter destined for one of the moons might still take 5 or 6 years, unless propelled by a revolutionary new engine like nuclear thermal propulsion. The past missions are our guide, proving what is possible with chemical rockets and gravity assists. They are the concrete data points on the graph of exploration. From Pioneer's first grainy images to Juno's stunning pole-to-pole views, each journey, whether short or long, has been a stepping stone in our understanding. The clock for each mission started ticking at liftoff, a moment of intense fire and noise, and ended years or just over a year later with a silent, precise encounter in the dark, a testament to the teams who calculated those paths and the spacecraft that survived them. This is the real meaning of travel time. It is the duration of a conversation between humanity and the cosmos, where the message is a spacecraft, and the reply is a torrent of data that takes years to arrive but changes our perspective forever. Looking back at that historical spread, from 13 months to 6 years, a natural question arises. If we can get to Jupiter in a little over a year, why do we ever choose to take 5 or 6? Why not just make every mission a speed demon like New Horizons? The answer lies in a brutal, unforgiving piece of mathematics that sits at the very heart of spaceflight, dictating every single design decision. It is called the rocket equation, and it imposes a cost on speed so severe that it forces mission planners into a constant, careful compromise. This is not about the price in dollars, though that is certainly a factor. This is about the physical price in fuel and mass, a relationship so punishing it is often called the tyranny of the rocket equation. To understand this, you have to think about how rockets work in the emptiness of space. They operate on the principle of conservation of momentum. To move forward, they throw mass backward at high speed. That thrown mass is the hot gas from their engines. The faster you can throw that mass out the back, the more push you get for every kilogram of fuel. This efficiency is measured as specific impulse. But the critical, tricky part is that the fuel needed to accelerate the spacecraft is itself part of the spacecraft's mass at the start. So you need fuel to push the fuel. This creates a snowball effect, or more accurately, a pyramid effect. Imagine you want to drive a car across a desert, but there are no gas stations. You have to carry all your fuel with you. To go twice as far, you do not just need twice the fuel. You need more fuel to carry that extra fuel, and then even more fuel to carry that asterisk fuel. Very quickly, the vast majority of your vehicle's weight at the start becomes nothing but fuel tanks. This is the core problem. The rocket equation, formulated by Konstantin Tsiolkovsky, provides the precise logarithmic relationship. In plain language, it says that to increase your final speed by a certain amount, you need to increase your initial mass by an exponential amount. Doubling your final speed might require not double, but perhaps 10 times or more the initial mass, depending on the engine efficiency. This is why cutting travel time in half is not a simple linear proposition. It is a monumental engineering challenge. A faster trajectory to Jupiter requires a higher departure speed from Earth. That extra speed demands a huge amount of extra propellant, but that propellant has mass, which requires an even bigger rocket to lift it, or forces you to shrink the spacecraft itself to a tiny minimal payload. This is the trade-off that defines every mission. Let us take the examples from history. New Horizons was incredibly fast. To achieve that, it was launched on a massive rocket, but the spacecraft itself was relatively compact and lightweight, shaped like a grand piano. It carried a powerful suite of instruments, but it was a flyby probe. It did not need to carry fuel to slow down and orbit Jupiter or Pluto. Its entire mass budget was optimized for that one high-speed push. Contrast that with Galileo. Galileo was a behemoth. It consisted of a large orbiter and an atmospheric probe. Its mission required it to carry a massive amount of fuel to fire its main engine for nearly 100 minutes to break into Jovian orbit. If engineers had tried to send Galileo on a 13-month trajectory like New Horizons, the fuel requirements would have been utterly insane. The launch rocket would have needed to be impossibly large, or Galileo would have had to be shrunk down to a mere skeleton of itself, carrying almost no science. So instead, they chose the 6-year gravity-assisted path. That longer trajectory required a much lower departure speed from Earth. It needed less fuel up front. The gravity assists from Venus and Earth provided the extra speed for free over time. This allowed the spacecraft to be heavier, more robust, and packed with fuel for its final orbital insertion. The mission designers traded time for mass. They accepted a long cruise so they could deliver a big, capable, fuel-laden spacecraft to its destination. This is the constant balancing act. On one side of the scale you have travel time. On the other, you have spacecraft mass, which includes the mass of the scientific instruments, the payload, and the mass of the fuel needed for the journey and any maneuvers at the destination. You cannot maximize both. You must find an optimum point. For robotic missions, time is often the resource which they're most willing to spend. A spacecraft can be put into hibernation for years. The scientists and engineers on Earth can wait. What they cannot do as easily is wait for a non-existent rocket large enough to launch a 5-ton orbiter on a 2-year trajectory. So, they design for the rockets that exist, which means accepting longer travel times to preserve the precious mass budget for science. This equation also explains why we use staging in rockets, and why gravity assists are so magical. Staging is a way to cheat the rocket equation a little bit. You drop off the empty fuel tanks and engines you no longer need, shedding dead weight so the remaining rocket does not have to accelerate it further. A gravity assist is even better. It provides a change in velocity without you having to carry and expel any of your own mass at all. It is a free boost, the ultimate loophole in the tyranny, which is why it is used whenever possible. Now consider what this means for the ultimate goal, sending humans. The human mission amplifies this problem by orders of magnitude. A crewed spacecraft is not a compact hibernating robot. It is a life support system. It needs shielding from radiation, which is incredibly heavy. It needs water, air, food, living space, exercise equipment, and waste recycling systems. The mass of a habitat for a multi-year journey is colossal. To send such a heavy object on a fast trajectory to Jupiter would require a propellant load of unimaginable proportions. Using the rocket equation, the numbers quickly become apocalyptic. This is why, with current chemical propulsion, a human mission to Jupiter is not just difficult, it is effectively impossible within any reasonable time frame. The only way to make it conceivable is to change the terms of the equation itself. You need either a much more efficient engine, one that throws mass out the back at vastly higher speeds, or you need to find a way to refuel in space. Or both. Nuclear thermal propulsion, which we touched on earlier, offers that better efficiency. By having a higher specific impulse, it needs less propellant mass to achieve the same change in velocity. This could reduce the propellant mass needed for a fast transit, making the overall spacecraft design less dominated by fuel tanks and more capable of carrying a heavy crew module. But even then, the trade-offs are severe. The rocket equation is a law, not a suggestion. It always demands its due. So when you look at the timeline of exploration, you're not just looking at a sequence of technological achievements, you're looking at a graph of optimized compromises. Each mission point represents the best possible balance its designers could find between the desire to get there quickly and the practical limits of mass and propulsion. The fast missions are lightweight and often single-purpose. The slower missions are heavier, more complex and more capable once they arrive. This economic reality shapes our entire approach to the solar system. It is why the inner planets, like Mars, are within nearer-term reach for the human exploration. The travel times are shorter, and therefore the propellant penalties for carrying heavy life support are less extreme. For Jupiter, the distance and time are so great that the equation pushes any human mission far into the future, waiting for a fundamental breakthrough. For now, our robotic emissaries follow the law of the rocket equation. They take the slow, economical routes, carrying their precious scientific payloads across the years. The journey time is the price we pay for doing substantial science at such a distance. We could send a tiny chip on a fast journey, but what could it do? Not much. So we choose to send a capable laboratory and we wait for it to arrive. This patience is written into the mathematics of spaceflight itself. Every gram counts, and every second of transit is a consequence of a deliberate choice to save grams. This is the hidden world of mission design, where teams of engineers argue over shaving ounces off a camera, because doing so might mean they can add an extra gallon of fuel, which might enable a slightly faster trajectory or a longer operational life at the destination. The rocket equation is the backdrop to all these decisions. It is the reason spaceflight is hard. It is the reason we cannot just go faster. It imposes a harsh reality where every increment of speed costs exponentially more. Understanding this makes the achievements of those past missions even more impressive. The engineers working on New Horizons squeezed every ounce of performance out of their launch vehicle to hit that 13-month timeline. The Galileo team performed orbital alchemy with gravity assists to deliver their massive orbiter within the limits of the Space Shuttle's cargo bay. They were all playing the same game, with the same unforgiving rules. The future of exploration depends on changing those rules. Advanced propulsion seeks to improve the specific impulse, the miles per gallon of a rocket engine, to soften the tyranny. But until such a time, the rocket equation remains the master accountant for every voyage beyond Earth. It tells us that in space, speed is the most expensive commodity there is, purchased not with money, but with impossible masses of fuel. So the next time you see a launch, remember that the brilliant flame you see is not just a symbol of power, it is the visible cost of defying a fundamental law of physics, a law that demands a heavy price for every mile per hour, a price that forces us to be patient, clever and humble as we reach for the planets. That brutal math of the rocket equation explains why we often choose slow economical paths, but it leads directly to another critical fork in the road once you actually approach Jupiter. Getting to the neighbourhood is one thing. Deciding whether to screech to a halt and move in, or just zoom past the house, is what truly defines the mission. This is the fundamental difference between a flyby and an orbiter, and it is a choice that ripples back through every single design decision, especially the travel time. Think of it like two different ways to study a city. A A flyby is like booking a high-speed train that races through the main station. You get a fantastic fleeting glimpse out the window. You can take some quick photos, sense the scale and atmosphere, but you're gone in seconds, unable to visit the neighbourhoods or talk to the locals. An orbiter, however, is like moving into an apartment. You take your time unpacking, you learn the daily rhythms, the weather patterns, the secrets of the different districts over months and years. Each approach has immense value, but they are fundamentally different endeavours. For a spacecraft, the moment of truth comes at closest approach. A flyby mission, like Pioneer, Voyager or New Horizons, is on a hyperbolic trajectory. It is going too fast to be captured by Jupiter's gravity. It uses Jupiter's gravity to bend its path, maybe even to gain speed, but it never intends to stay. It screams past at tens of thousands of miles per hour, collecting a furious rush of data during the brief encounter. And then it is gone forever into the dark. This is a relatively simple proposition from a propulsion standpoint. All the fuel and energy is spent on the front end, getting it up to that incredible speed. No fuel is needed to slow down at Jupiter. This simplicity is what allows for those blisteringly fast travel times of 13 months to 2 years. The spacecraft can be lighter, focused on robust instruments for a short, intense period of observation. But if you want to stay, to become a temporary moon of Jupiter, everything changes. You must perform one of the most critical and nerve-wracking manoeuvres in deep space exploration, Jupiter Orbit Insertion, or JOI. This is the moment where the spacecraft, having fallen for years toward the giant planet, must slam on the brakes at exactly the right instant. It is a controlled, planned crash into the wall of Jupiter's gravity, using fire to avoid a literal crash. As the spacecraft is pulled in by Jupiter's immense gravity, it is accelerating to phenomenal speeds. To be captured, it must radically reduce its speed relative to Jupiter. It does this by turning its main engine to face the direction of travel and firing it for a long, sustained burn. This burn opposes its velocity, slowing it down just enough that Jupiter's gravity can grab it and pull it into a loose initial orbit. The Galileo orbiter's JOI burn lasted an incredible 96 minutes. Juno's burn was about 35 minutes. During this time, the spacecraft is on its own. With a communication delay of over 50 minutes, engineers on Earth cannot control it in real time. The sequence is pre-programmed, and the spacecraft's computer must execute it flawlessly. If the burn fails, or is too short, the spacecraft simply whips around Jupiter and is thrown back out onto a path into deep space. A multi-billion-dollar mission ending in utter failure. This single maneuver therefore dictates an enormous amount about the entire mission design. First, and most obviously, the spacecraft must carry all the fuel for this burn from Earth. Remember the rocket equation? That fuel has mass. To accelerate that mass of fuel on the journey from Earth requires even more fuel at launch. So choosing to be an orbiter automatically makes your spacecraft much heavier in terms of propellant from the very beginning. This heaviness often forces the choice of a slower, more fuel-efficient trajectory to Jupiter, like a Hohmann transfer or a gravity assist tour. You're trading a fast arrival for the ability to carry the braking fuel. Second, the need to perform JOI influences the approach trajectory itself. An orbiter cannot approach Jupiter at just any angle or speed. It must arrive on a path that allows for a feasible insertion burn. This often means aiming for a slower approach velocity, which again points toward those longer, lower energy trajectories. A flyby can come screaming in from almost any direction. An orbiter has to be much more polite and orderly in its approach. This is a primary reason why Galileo took 6 years and Juno took 5, while the flybys took so little time. The orbiters were on patient, fuel-efficient paths that delivered them to Jupiter at a manageable speed for the braking maneuver. Furthermore, once you're in orbit, the story is not over. You will likely need to perform additional, smaller engine burns to tighten your orbit, adjust its shape, or move into orbit around a specific moon. All of this requires more fuel, which, you guessed it, had to be brought from Earth. So the propellant tank for an orbiter is a huge, heavy component, dominating its mass budget. This leaves less mass for scientific instruments compared to a flyby of the same launch weight, though the trade-off is considered worth it for the years of close-up study. Let us make this concrete with our historical examples. The Voyager missions were the ultimate flybys. Their goal was a grand tour to see as much as possible as quickly as possible. They carried enough fuel for course corrections, but not for planetary capture. Their spectacular success gave us our first detailed global views and unleashed a tidal wave of discoveries, but they were gone in a flash. Galileo was the first orbiter. Its complex 6-year journey was all about delivering that heavy orbiter and its probe with enough fuel to stop. The reward was years of data, the first long-term study of the Jovian system, including the astonishing revelation of ocean worlds like Europa. Juno followed as a specialised orbiter, taking 5 years to get there and carrying the fuel for its braking burn and subsequent orbital adjustments. Its polar orbit allowed it to study Jupiter's interior and auroras in ways a flyby never could. So, the choice between these two mission architectures answers different scientific questions. Flybys are perfect for reconnaissance, for first looks, or for using a planet as a gravitational stepping stone to elsewhere. They are relatively fast and cheap, and they can visit multiple targets. Orbiters are for deep, sustained investigation. They study changes over time, map entire worlds, and act as long-term observatories within the system. The travel time is an investment in that long-term payoff. For destinations like Jupiter's moon Europa, an orbiter is essential. A flyby might snap a few pictures of the icy surface, but understanding its subsurface ocean requires repeated close passes with radar and magnetometers over months or years to probe its depth and salinity. That is why the upcoming Europa Clipper mission, while it will not orbit Europa directly due to radiation, will orbit Jupiter in a way that allows for dozens of dedicated Europa flybys over its mission lifetime. It is a hybrid approach, but one that still requires a significant orbital insertion burn at Jupiter, and thus a longer cruise time. In the end, the question of how long does it take to get to Jupiter is inseparable from the question of what will you do when you arrive. The answer to the second question determines the answer to the first. If the goal is a quick hello, we can get there in a hurry. If the goal is to move in and stay a while, we must pack a much heavier suitcase, and that means taking the slower, more economical flight. This dichotomy will continue until we develop propulsion systems so efficient that the mass penalty for carrying braking fuel becomes trivial. Until that day, the patient orbiters will continue to take the scenic route. Their longer journeys are a necessary prelude to an in-depth conversation with a giant. The discussion of orbiters versus flybys centres on robotic explorers, machines we can put into hibernation for years and ask to wait patiently. But when we shift the conversation to human beings, every single parameter we have discussed so far, travel time, propulsion, trajectory, orbital insertion, explodes in complexity. Sending people to Jupiter is not just a harder version of sending a robot, it is a challenge of such a different magnitude that it belongs to a separate category of thought altogether. The core reason is that a human crew transforms the spacecraft from a disposable instrument into a fragile, self-sustaining world, and the length of the journey becomes an enemy to be defeated, not a parameter to be optimized. Let us start with the most immediate and lethal difference: radiation. Jupiter possesses the most powerful radiation belts in the solar system, a torus of charged particles accelerated by the planet's immense magnetic field. For a robotic probe like Juno, this is a severe but manageable engineering problem. We use hardened electronics, shield critical components, and design orbits to minimize exposure. For a human crew, it is a showstopper. The radiation levels in Jupiter's magnetosphere are not just dangerous, they are quickly lethal. A spacecraft carrying humans would need massive shielding, likely many tons of water or specialized materials, just to protect the crew during the flyby or orbital pass. This shielding mass is dead weight that must be accelerated and decelerated, slamming headfirst into the rocket equation we just discussed. But the radiation problem is not just at Jupiter. The journey itself, through the deep space of the inner solar system and across the asteroid belt, exposes the crew to a constant background of cosmic rays, high-energied particles from outside our solar system. There is no magnetic field out there to deflect them. A multi-year journey, even before reaching Jupiter's extreme environment, would accumulate a radiation dose that significantly increases cancer risk and could cause acute radiation sickness during solar particle events. This means the entire spacecraft, the habitat, must be a shielded bunker. The mass implications are staggering. Next, consider life support. A robot needs power and occasional commands. A human needs thousands of pounds of water, food and air every year. For a journey measured in years, you cannot possibly carry all of it. You need a nearly perfect closed-loop system that recycles every drop of water and every molecule of oxygen. The International Space Station has such systems, but they require constant maintenance, resupply from Earth, and are far from 100% efficient. For a mission to Jupiter, you would need a system of unprecedented reliability and efficiency, capable of running for years without spare parts from home. A single failure in the water recycler or the carbon dioxide scrubbers could doom the mission. This system itself adds enormous mass, complexity, and power requirements. Then there is the human body itself. We are not built for zero gravity. On the ISS, astronauts exercise for hours each day to mitigate muscle atrophy and bone density loss. Even with that, they return to Earth weakened and require rehabilitation. A journey to Jupiter, likely lasting 3 to 6 years with current propulsion ideas, would subject the crew to microgravity for a duration far beyond any current experience. The physiological degradation could be so severe that upon arriving at Jupiter, the crew might be too weak to perform their duties, and upon returning to Earth, they might never fully recover. This pushes the mission design toward including artificial gravity, likely created by spinning a section of the spacecraft. Imagine a small habitat module tethered to a spent rocket stage, rotating to create centrifugal force. This introduces a whole new world of engineering complexity, spinning joints, balance issues, and potential for motion sickness. It is doable, but again it adds mass, moving parts, and risk. Psychology is another monumental hurdle. Imagine being locked in a small metal can with a handful of other people for 5 years. You're utterly isolated. A conversation with Mission Control has a delay of over an hour round trip, so real-time help or comforting chats with family are impossible. You're truly on your own. The monotony, the confinement, the stress of potential system failures, and the sheer distance from home present a psychological challenge we are only beginning to understand through simulations like High Seas. Crew selection and in-mission psychological support would be critical, but the environment itself is inherently hostile to mental well-being. All of these factors, radiation shielding, life support mass, artificial gravity, catapult the mass of the spacecraft into the hundreds of tons, perhaps thousands. Now, recall the rocket equation. To accelerate this colossal, shielded, life-supporting habitat to a speed that would make the journey even remotely acceptable for humans, let us say under 3 years, you would need a propellant load that is simply unimaginable with chemical rockets. This is why all serious concepts for human missions beyond Mars involve advanced propulsion. Nuclear thermal propulsion, as discussed earlier, is the near-term candidate. It could potentially cut the Earth to Jupiter transit time to around 2 to 3 years. That is still a very long time, but it begins to enter a realm where the other problems, while still gargantuan, might be tackled with staggering investment and innovation. Even with nuclear propulsion, you're not looking at a direct mission to orbit Jupiter. The radiation and the fuel needed to break into orbit would likely be prohibitive. A more plausible first human mission to the Jovian system would be a flyby, perhaps swinging by Jupiter to use its gravity to reach Saturn, or to enter a trajectory that returns to Earth. This was studied in the 1960s and 70s with projects like the Jupiter Flyby or Grand Tour concepts. The crew would get a magnificent close-up view, but they would not stop. They would be on a very long free return trajectory around the Sun. Another concept might involve setting up a base on one of Jupiter's moons, like Callisto. Callisto is far enough from Jupiter's radiation belts to be somewhat more manageable. But then you face the challenge of landing, setting up a base, and surviving on an icy, airless world. The journey there is still the primary barrier. So, when we talk about travel time to Jupiter for humans, it is not just a number. It is the central variable that dictates feasibility. A 6-year journey with chemical propulsion is likely a biological impossibility due to radiation and microgravity effects. A 2 to 3 year journey with nuclear propulsion might be on the edge of biological possibility, with heavy shielding and artificial gravity, but it remains a monumental engineering and financial challenge. This is why the current and near-future focus for human exploration is squarely on the Moon and Mars. Mars is close enough that a round trip, while still taking years, can be envisioned with reasonably extended exposure to space's hazards. It is the next logical step. Jupiter, for humans, is a dream for the distant future, perhaps the latter half of this century at the very earliest. It requires technologies we have not yet fully mastered, and a level of investment we have not yet mustered. The travel time, therefore, is the great filter. It forces us to develop new propulsion to shrink it, new shielding to survive it, and new systems to sustain life throughout it. Until we can meaningfully reduce that time and mitigate its effects, Jupiter will remain the exclusive domain of our robotic avatars, who report back whispers of a giant world that, for now, is just too far for flesh and blood to reach. The immense challenges of sending humans to Jupiter make one thing very clear. For the foreseeable future, the real action, the most profound discoveries will not be at the giant planet itself, but in the intricate dance of its moons. When we talk about going to Jupiter in a scientific sense, we are often using the planet as a gravitational anchor, a central bus stop for missions whose ultimate destinations are worlds like Europa, Ganymede, and Callisto. These are not mere rocks, they're complex dynamic worlds, and some harbour a secret that drives our entire exploration agenda. Vast global oceans of liquid water hidden beneath icy shells. This transforms the journey from a trip to a gas giant into a pilgrimage to a potential cradle of alien life. The most compelling of these destinations is Europa. Slightly smaller than Earth's moon, its surface is a cracked, criss-crossed landscape of ice, stained with reddish-brown material. It looks like a giant cracked egg. But the most important thing about Europa is what lies beneath that icy crust. A global saltwater ocean, estimated to be perhaps 60 miles deep, containing more than twice the water of all Earth's oceans combined. This ocean is kept liquid by tidal heating. As Europa orbits Jupiter in an elliptical path, the giant planet's immense gravity squeezes and stretches the moon, generating internal friction and heat. This heat prevents the water from freezing solid, creating a potentially habitable environment. Where there is liquid water, energy, and the right chemistry, there is the possibility of life. This is not just speculation. It is a powerful scientific hypothesis that justifies billion-dollar missions. Ganymede, the largest moon in the solar system, even larger than the planet Mercury, has its own subterranean ocean, likely sandwiched between layers of ice. Callisto may also have a subsurface ocean. These moons are not just geological curiosities, they're biological hope chests. So, a mission to land on Europa, for instance, is not a simple extension of orbiting Jupiter. It is a mission of staggering complexity that adds multiple layers to the travel timeline. First, you must get to the Jovian system, which as we know takes years. Then, you must perform Jupiter orbit insertion to become a satellite of the planet. But you are not done. You are now in a wide orbit around Jupiter. To study Europa, you need to get much closer. This requires a series of additional engine burns, using precious fuel to change your orbit and lower its energy, eventually entering an orbit that regularly brings you close to Europa. This process, called orbital tuning or moon tour sequencing, can take many months. Only after that can you even contemplate a landing. A lander mission adds another entire spacecraft, another set of propulsion and guidance systems. The lander would separate from the orbiter, fire its own descent engines to cancel its orbital velocity, and attempt a soft touchdown on an unknown, potentially treacherous icy surface. Every single one of these steps, interplanetary cruise, Jupiter capture, orbital tuning, lander descent, requires propellant, and all that propellant must be launched from Earth, making the rocket equation an even more tyrannical master. This cascading complexity is why we have not landed on Europa yet. It is why the upcoming flagship mission is called Europa Clipper, not Europa Lander. The Clipper mission is designed to perform detailed reconnaissance. It will orbit Jupiter in a long, looping path that brings it close to Europa dozens of times, flying through plumes of water vapour that may erupt from the cracks, analysing the surface composition with powerful instruments, and using ice-penetrating radar to map the subsurface ocean's depth and salinity. It is the essential scout, gathering the data we would need to someday, safely, send a lander to the most promising location. And even this scout mission, a flyby-centric orbiter, has a planned cruise time of about 5.5 years. A future lander mission would be even more massive and complex, likely requiring an even more efficient trajectory or a heavier launch vehicle, potentially keeping the travel time in that 5 to 6 year range. The radiation environment around Jupiter adds another cruel twist. Europa orbits within Jupiter's ferocious radiation belts. A spacecraft, and especially a lander, must be designed to survive that onslaught. This often means adding shielding, which is mass, or designing the trajectory to limit radiation exposure. which might mean fewer close flybys or a faster exit from the high radiation zones. For a lander, which must survive on the surface for perhaps days or weeks, radiation hardening is a supreme challenge. The electronics must be incredibly robust, or they must be buried deep within shielding on the lander itself. All of this design work is done to answer the most fundamental question we can ask. Are we alone? The potential discovery of life, even microbial life in Europa's ocean, would be a paradigm-shattering event. It would prove that life is not a fluke unique to Earth, but a common process in the cosmos wherever the conditions are right. This is not just planetary science, it is a quest for biological meaning. These profound stakes make the long travel time not just acceptable, but a necessary investment. Scientists and engineers are willing to spend a career shepherding a mission from conception to data return because the payoff could redefine our place in the universe. The journey time becomes part of the narrative, a long, silent prelude to a moment of potential revelation. Compare this to a mission to, say, an asteroid. The science is valuable, but it does not carry the same transformative weight. For Europa, we accept the years of crews, the complexity of orbital operations, and the technical nightmares of radiation because the target is just that important. It is the holy grail of contemporary solar system exploration. This focus also changes how we think about arrival. For the Voyagers, arrival at Jupiter was a frenetic, days-long flurry of activity followed by a permanent goodbye. For an Europa-focused mission, arrival at Jupiter is merely the end of the first act. The second act is the orbital tour, a careful year-long dance using gravity assists from the moons themselves to shape the orbit without excessive fuel use. This is an art form in itself, a delicate game of celestial billiards, where Ganymede might be used to lower the orbit to encounter Europa, or Callisto might be used to adjust the inclination. The spacecraft becomes a member of the Jovian system, its path woven into the gravitational fabric of the moons. This extended operational phase after the long cruise is what makes the data so rich. You can observe how Europa's surface changes over time, track the movement of ice, and wait for a chance plume eruption. You get context, not just a snapshot. So, when you ask how long it takes to get to Jupiter, for a mission to the moons, you must ask a follow-up. How long until it starts its primary science? The answer might be 5.5 years to Jupiter, plus another 6 months to a year to get into the correct orbit for the moon tour. The patience required is immense, but it is built into the scientific method. We are not tourists, we are detectives, and the crime scene is 480 million miles away. The clues have been waiting for billions of years. We can afford to wait a few more years to get the investigation right. This long-term perspective is what separates robotic exploration from human. A robot does not age, does not get bored, does not fear radiation. It can wait in silent hibernation for years, then wake up and perform flawlessly. It is the perfect tool for this kind of long-haul, high-stakes investigation. The travel time, therefore, is not a barrier to the science. It is a parameter around which the science is designed. Missions are planned with cruise phases that include instrument checkouts, calibration, and even supplemental science observations of other asteroids or the interplanetary medium. The journey is part of the mission life cycle. In the end, the moons are the prize. Jupiter, for all its majestic fury, is ultimately a backdrop, a gravitational guardian for worlds that may hold secrets about life's tenacity. The travel time to get there is the price of admission to the greatest show in the solar system, a show where the main act might be happening in the dark, warm waters beneath the ice, waiting for us to listen. The search for life on moons like Europa introduces a formidable and non-negotiable hurdle that every spacecraft must face, a pervasive danger that shapes mission design perhaps more than any other factor except gravity itself: radiation. Jupiter's radiation belts are the most intense in the entire solar system, a swirling donut of trapped high-energy particles that makes the Van Allen belts around Earth look like a gentle breeze. This environment is not merely a background hazard, it is an active, destructive force that directly influences how we get to Jupiter, what paths we take, and how long we can survive there. To understand why, picture Jupiter's powerful magnetic field. This field is generated by currents within the planet's layer of metallic hydrogen, and it is staggeringly strong, about 20,000 times stronger than Earth's. This magnetic field acts like a colossal particle accelerator. It captures charged particles, mostly electrons and protons from the solar wind, but also ions from volcanic Moon Io, and whips them around at nearly the speed of light. These particles become trapped, bouncing between the magnetic poles, forming vast toroidal belts of radiation that envelop the planet and extend out past the orbit of Europa. For a spacecraft, this radiation is a silent killer. It does not just pass through, it interacts. High-energy particles can slam into electronics, causing bit flips, where a 0 in a computer's memory suddenly becomes a 1, or vice versa. This can corrupt data or, in a worst-case scenario, issue a faulty command that could doom the mission. Over time, the cumulative dose degrades solar panels, reducing their power output. It can damage sensitive scientific instruments, fog up camera lenses, and weaken materials. A spacecraft venturing into this zone is essentially undergoing a prolonged, brutal stress test. This reality forces engineers to make critical choices that directly affect the travel time and trajectory. First, they must harden the spacecraft. This involves using radiation-tolerant electronic components, shielding critical systems with materials like tantalum or tungsten, and designing redundant systems so that if one circuit fries, another can take over. The Juno spacecraft, for example, has a shielded vault, a titanium box about the size of a car trunk that houses its most vital computer brains. This hardening adds weight, and as we know, weight is the eternal enemy. But the influence of radiation on travel time is more subtle than just adding shielding mass. It profoundly affects the trajectory and the mission timeline after arrival. A spacecraft destined to orbit Jupiter, especially one aiming to study the inner moons, cannot simply take the fastest path and then park itself in a convenient orbit. It must plan its approach and final orbit to minimize cumulative radiation exposure. This is why Juno uses a highly elliptical polar orbit that swoops in for a close pass over the poles and then races back out, spending very little time in the most intense regions of the radiation belts. This orbit was chosen specifically to prolong the spacecraft's life. Even with this careful planning, Juno's mission lifespan is limited by radiation damage. It was designed for a specific number of orbits before degradation would become too severe. For a mission like the upcoming Europa Clipper, radiation dictates the entire operational concept. Europa orbits within the heart of the radiation belts. If Clipper attempted to orbit Europa itself, the radiation would destroy it in a matter of weeks. So, instead, the mission designers chose a clever orbit Jupiter flyby Europa strategy. Clipper will be placed in a long orbit around Jupiter that only briefly dips into the high radiation zone during each close flyby of Europa. It will collect a torrent of data during each quick pass, then retreat to a safer distance to transmit that data back to Earth. This strategy extends the spacecraft's operational life from months to years, but it is a direct concession to the radiation environment. It means the mission's primary science phase is a series of brief, intense encounters over a long period, rather than a continuous observation from a close orbit. Therefore, the radiation does not necessarily lengthen the cruise to Jupiter, but it dramatically shapes what happens after arrival, often requiring more complex orbital choreography that can take additional months to establish. Now, consider what this means for the dream of landing on Europa. A lander must not only survive the transit and the Jovian radiation environment during its approach and descent, but it must also operate on the surface. While the ice crust provides some shielding, the surface of Europa is still a high radiation environment. Any lander would need to be incredibly robust, with its own heavy shielding, or it would have to execute its science mission very quickly before its systems succumb. This pushes the design toward either extreme hardening or extreme simplicity, both of which influence the mass and complexity of the entire mission from the launch pad onward. For human exploration, as previously touched upon, the radiation belts present a wall. The dose accumulated during even a fast flyby through the belts, without the protection of a planetary atmosphere or magnetic field, would be fatal. Any crewed capsule would require shielding so massive that, with current propulsion, it could never get off the ground. This is perhaps the single greatest technical showstopper for human journeys to Jupiter, even more prohibitive than the travel time itself. Solutions like using water or fuel as a radiation shield have been theorized, or creating magnetic shielding akin to a mini-magnetosphere around the spacecraft, but these are concepts for the far future. So, the radiation environment of Jupiter is a pervasive design constraint. It is a filter that selects for certain kinds of missions and forbids others. It forces engineers to be clever, to choose circuitous orbits, to accept limited operational lifetimes, and to invest in heavy, protective boxes for their electronics. It turns the space around Jupiter from a void into a corrosive soup that etches away at our machinery. This also means that when we calculate how long a spacecraft will last at Jupiter, we are not just counting fuel or battery power, we are counting rads, the units of radiation absorption. The mission clock is ticking down from the moment the spacecraft enters the belts. This adds a layer of urgency to the science operations once there. Every pass through the radiation zone is costly, so every flyby must be exquisitely planned to gather the maximum data. There is no time for wasted moments. This pressure influences the onboard automation. The spacecraft must be smart enough to adjust its observations in real time if a target of opportunity, like a potential plume on Europa, appears, because waiting for commands from Earth would mean missing the shot. In a very real sense, Jupiter's radiation belts are the gatekeeper. They guard the secrets of the planet and its moons, demanding a toll of engineering ingenuity and operational caution. They ensure that our exploration is, for now, conducted by hardened robotic scouts who can venture where we cannot. They lengthen not the journey to Jupiter, but the careful dance-like approach within the system itself. A mission cannot just rush in, it must tiptoe through a minefield of particles, planning each step to avoid an early demise. This transforms the concept of arrival. You have not truly arrived at Jupiter until you have learned to survive in its house, and its house is filled with invisible destructive fire. So, the next time you see a stunning image from Juno, remember that it was taken by a camera peering out from inside a titanium vault between sips of a deadly bath of radiation. A testament not just to human curiosity, but to our ability to protect a fragile bundle of circuitry long enough to steal a glimpse before the environment claims it. The travel time to Jupiter is just the prelude. The real race against time begins when you get there, and the opponent is an invisible storm that never ceases. That radiation environment underscores a more fundamental and pervasive truth about Jupiter. It is profoundly, staggeringly far away. This distance does more than just lengthen the journey and create a hazardous particle storm. It severs the immediate connection we take for granted with every other machine we operate. On Earth, or even in low orbit, we expect instant response. A rover on Mars tests that expectation, with delays of up to 20 minutes. But Jupiter exists in a different realm of remoteness, where the very speed of light feels slow, and this communication delay becomes a defining characteristic of the mission, reshaping operations and deepening the sense of isolation. The problem is simple physics. Radio waves, which carry our commands and the spacecraft's data, travel at the speed of light, which is about 186,000 miles per second. That is impossibly fast here on Earth. But against the scale of the solar system, it is a crawl. When Jupiter is at its closest to us, a signal still takes about 35 minutes to make the one-way trip. When Earth and Jupiter are on opposite sides of the Sun, that one-way light time balloons to over 50 minutes. That means a simple round-trip communication, sending a command and receiving confirmation that it was received, can take well over an hour and a half. For critical operations like the Jupiter orbit insertion burn, this is an eternity. This delay makes real-time control an absolute impossibility. You cannot joystick a spacecraft into orbit around Jupiter. You cannot troubleshoot a sudden problem in a live conversation with the probe. This forces a complete rethinking of how a mission is run. The spacecraft must be incredibly autonomous. It is not just a remote-controlled drone, it is a robotic ambassador with a pre-programmed brain, capable of making its own decisions in real time. Before a critical event like flying through the turbulent radiation environment near a moon, engineers on Earth will upload a detailed sequence of commands, a script that tells the spacecraft what to do, when to do it, and how to react to certain contingencies. The spacecraft then executes that script on its own, without any further input from Earth. It must monitor its own health, switch to backup systems if it detects a failure, and even adjust its observations on the fly if it sees something interesting. This level of autonomy requires sophisticated software and ultra-reliable hardware, because there is no one to call for help. This operational reality stretches the perceived time of the mission in a unique way. A problem that might be solved in a day with a satellite in Earth orbit can become a week-long crisis at Jupiter. Here is how it plays out. The spacecraft encounters an anomaly and puts itself into a safe mode. It stops all science activities, points its antenna at Earth, and waits for instructions. The engineers on Earth notice the loss of signal. They wait. 43 minutes later, the signal detailing the safe mode event arrives. They analyse the data for several hours. They then develop a plan, a carefully crafted set of commands to diagnose and recover the spacecraft. They transmit those commands. Another 43 minutes pass as the signal travels out. The spacecraft receives the commands, executes them, and sends back a status report. Another 43-minute wait. What was a few hours of work in terms of human thought has just consumed 4 or 5 days of calendar time. This slow-motion troubleshooting is the norm. It injects a necessary patience into mission operations, a rhythm dictated not by human schedules, but by the geometry of the solar system. For the scientists, this means the thrilling data from a close flyby does not come pouring in immediately. The spacecraft might spend hours or days after the encounter playing back its recorded data bit by bit across the vast distance. The first images might trickle in as low-resolution thumbnails, with the full, stunning details arriving days later. The anticipation is drawn out, stretched by the speed of light itself. Now, amplify this effect for a human crew. The psychological impact of such a communication delay cannot be overstated. For a crew on a journey to Jupiter, contact with Earth would be reduced to what is essentially email. A video call would be pointless. You would be talking to a recording from over an hour ago. Any question you ask Mission Control would take at least an hour and a half to get an answer. In an emergency, you're truly on your own. This isolation is deeper than any experienced by polar explorers or astronauts on the International Space Station. They at least have near-instant communication for comfort and consultation. A crew bound for Jupiter would experience a level of disconnect from humanity never before felt. They would watch Earth shrink to a pale blue dot, and then they would feel the silence. A silence enforced by physics. Every conversation with loved ones would be a series of monologues sent into the void, the replies arriving long after the moment has passed. This fundamentally changes the nature of the expedition. It becomes less a mission controlled from Earth and more a voyage of a self-contained ark. The crew would have to function as a completely independent society, capable of handling every medical, technical and interpersonal crisis without outside guidance. This communication barrier is perhaps as daunting as the radiation or the travel time for human aspirations. For our robotic probes, this delay is a manageable constraint, a puzzle for software engineers and operations planners. They build the autonomy, they practice the slow-motion simulations, and they learn to think days ahead. It makes the missions more complex and risky, but it is a solved problem. We have been doing it for decades, yet it constantly reminds us of the true scale of our exploration. That hour-long delay is a direct measure of the distance. It is a tangible operational manifestation of the gulf we have crossed. Every time a team at the Jet Propulsion Laboratory waits for a signal from Juno, they are literally waiting for the present to catch up with the spacecraft's past. The spacecraft's now is our 43 minutes ago. This time lag means we're always looking into the recent history of the probe, never its immediate state. This also affects navigation. When we track the spacecraft's position by its radio signal, we are seeing where it was tens of minutes ago. To fire its engine for a course correction, we must calculate where it will be in the future based on where it was in the past. It is a predictive game of extraordinary precision. In a very real sense, the communication delay integrates itself into the fabric of the mission timeline. It is not just the 5-year cruise, it is the 5-year cruise plus the cumulative months of light time delays for every command and data return. It slows the pace of discovery to a stately, deliberate cadence. There is no rushing it. This forced patience, however, has a benefit. It demands rigorous planning and foresight. It eliminates the possibility of impulsive reactive decisions. Every command sequence is pondered, tested and reviewed, because a mistake cannot be instantly corrected. This carefulness breeds a form of discipline that likely makes the missions more robust. So, while the radiation belts are a physical battlefield for the spacecraft's hardware, the communication delay is a cognitive battlefield for the team on Earth. They must project their intentions across a gulf of both space and time, trusting the machine they built to carry out their will long after the instruction have left the antenna. It is a testament to human ingenuity that we have made this work so well. that we can guide a fragile vessel to a precise point next to a giant planet with instructions we sent over a month prior, knowing that by the time the signal arrives our calculations will still be correct. The delay, therefore, is more than a hurdle. It is the central condition of deep space exploration. It defines the relationship between the explorer and home base. It turns the mission from a remote operation into a dialogue with a time traveller, where every question and answer spans the past and the future. When we finally receive that long-awaited signal confirming a successful orbit insertion, we are not just celebrating an engineering triumph over distance. We are celebrating a triumph over time, proving that our planning and our patience can bridge the hour-long silence that separates us from the worlds we yearn to understand. The profound communication delay underscores a central truth. To truly master the outer solar system, we must overcome not just the barrier of distance, but the barrier of time. The current paradigm of multi-year cruises, while successful, confines our reach and limits our ambitions, especially for human exploration. The future of journeys to Jupiter, therefore, hinges on a revolution in how we push spacecraft through space. We are talking about moving beyond the brief, fiery burst of chemical rockets to sustained, powerful propulsion that could slash travel times from years to mere months, transforming Jupiter from a distant, once-in-a-career target into a more accessible destination. This is the realm of advanced propulsion, and while some concepts sound like science fiction, they are grounded in serious physics and active research. The starting point for this future is a technology that has been studied for decades, but never fully realized for spaceflight: nuclear thermal propulsion, or NTP. Imagine replacing the chemical combustion chamber of a rocket with a compact nuclear reactor. Instead of burning fuel, you pump a light propellant like liquid hydrogen through the reactor core, where it is heated to extreme temperatures, thousands of degrees, before expanding out of a nozzle. The key advantage is efficiency, measured as specific impulse. Because the hydrogen is heated by a separate energy source, and not by chemical reaction, it can be ejected at much higher speeds. This means you get more thrust per kilogram of propellant. An NTP engine could have roughly double the efficiency of the best chemical engines. For a mission to Jupiter, this is a game changer. It would not necessarily provide the instantaneous, bone-crushing thrust of a chemical liftoff from Earth. You would likely still use chemical rockets for that initial kick. But once in space, the nuclear thermal engine could ignite. It could perform a sustained burn lasting minutes or even hours, accelerating the spacecraft to a much higher cruise speed. Then it could shut down, with the spacecraft coasting at that higher velocity. Critically, upon approach to Jupiter, it could fire again to slow down for orbital insertion. This ability to perform major propulsive maneuvers both at the beginning and the end of the journey enables faster, more direct trajectories. Studies suggest a robust nuclear thermal propulsion system could reduce transit time to Jupiter to around 2 years, possibly less for flybys. This is not months, but it is a dramatic cut from the 5 to 6 year cruises of current orbiters. It represents a crucial stepping stone. The technology was actually developed and ground tested in the United States under the NERVA program in the 1960s and 70s, proving the basic engineering was sound. Today, there are renewed efforts and funding to develop and demonstrate modern NTP systems with an eye toward lunar and Mars missions. For Jupiter, it would be transformative, making orbiter missions quicker and more flexible, and bringing crude flyby concepts slightly closer to reality. But the real leap toward month-long transits requires something even more efficient and powerful: nuclear electric propulsion, or NEP. Here the concept is different. A nuclear reactor, fission for now, fusion in a more distant future, is used solely to generate electricity, a lot of it. That electricity then powers extremely high-performance electric thrusters, like advanced ion or plasma drives. Remember, electric thrusters have very high specific impulse. They are very fuel efficient, but they are traditionally limited by the amount of electrical power available, usually from solar panels. At Jupiter, sunlight is weak, making large solar panels a challenge. A nuclear reactor solves the power problem utterly. It provides megawatts of continuous electrical power, enabling clusters of powerful electric thrusters to operate continuously for years. A spacecraft with an NEP system would not follow a brief burn, long coast trajectory. It would thrust continuously, gently but persistently for most of the journey. It would accelerate halfway to Jupiter, then flip and decelerate the other half. This constant acceleration profile could enable remarkably fast transits. While the acceleration might be mild, perhaps a tiny fraction of Earth's gravity, over months it would build up tremendous speed. With sufficiently powerful reactors and thrusters, a trip to Jupiter could conceivably be reduced to 6 to 9 months. This is the realm where robotic missions could become remarkably rapid, and where human missions start to look biologically plausible, as the shorter transit reduces radiation exposure and microgravity effects. The challenges, however, are immense. You need a compact, safe, space-rated nuclear reactor that can operate reliably for years. You need to manage the waste heat from the reactor and the thrusters, which requires massive radiator panels. You need extremely durable electric thrusters that can operate for tens of thousands of hours. The development is complex and expensive, but the payoff would be a true highway system for the solar system. Then we look to the true horizon, fusion propulsion. If we could achieve controlled nuclear fusion, harnessing the power of the sun in a compact reactor, the energy densities become almost unimaginable. Fusion rockets could provide both high thrust and extremely high specific impulse, the holy grail of propulsion. Concepts like the Daedalus study, conducted by the British Interplanetary Society in the 1970s, envisioned unmanned fusion-powered probes that could reach nearby stars in a human lifetime. For Jupiter, a fusion rocket could reduce travel time to weeks or months, with comfortable acceleration for a crew. It remains a distant dream, reliant on a breakthrough in contained fusion that has eluded us for decades, but it represents the ultimate goal. There are also non-nuclear, but still revolutionary concepts. The solar sail, which uses the pressure of sunlight for thrust, is a reality for small missions within the inner solar system. For fast journeys to the outer planets, however, sunlight pressure becomes too weak. The solution could be laser or microwave sailing. Imagine a gigantic array of lasers stationed in Earth orbit or on the Moon, beaming focused energy onto a gigantic ultralight sail on a distant spacecraft. This could accelerate a lightweight probe to a significant fraction of the speed of light, making a flyby of Jupiter a matter of days, though stopping would be another problem entirely. For more substantial craft, beamed energy concepts face enormous engineering hurdles. The common thread with all these advanced systems is that they decouple the energy source from the propellant. Chemical rockets combine them. The fuel is both the energy source and the expelled mass. Advanced systems separate them. A nuclear reactor or a laser provides the energy, and a separate lightweight propellant like hydrogen or xenon is expelled. This is the key to breaking the tyranny of the rocket equation, allowing for much higher exhaust velocities and thus much more efficient use of propellant mass. The impact on mission design would be profound. With travel times measured in months instead of years, the entire risk profile changes. Radiation exposure for both electronics and potential crews is reduced. The need for perfect once every 13-month launch window softens. With enough propulsion power, you can leave more often and take more direct routes. The spacecraft itself can be designed differently. You might not need extreme long-term reliability for a decade-long mission. A 2-year mission with a 6-month cruise is a different engineering problem. Science missions could be more responsive. If a new phenomenon is observed at Jupiter, a new probe could be dispatched on a fast track to investigate. For human exploration, this is the essential enabling technology. A 6-month to 1-year journey to Jupiter, while still monumental, enters a realm where we can conceptualize countermeasures for radiation and microgravity. It transitions from impossible to merely extraordinarily difficult. The development path is clear, though steep. Nuclear thermal propulsion is the nearest term step, likely for cislunar space and Mars. Success there would build the confidence and technological base for more powerful nuclear electric systems. Each step shrinks the effective size of the solar system. So when we ask how long it will take to get to Jupiter in the future, the answer is not fixed by orbital mechanics alone. It is fixed by our investment in propulsion technology. The 5-year journey of today is not a law of nature. It is a snapshot of our current capabilities. As we innovate, that timeline will compress. The giant planet shrouded in radiation and mystery awaits not just our patience, but our ingenuity. The clock is ticking not on the mission, but on us, to develop the engines that will finally allow us to cross the Great Gulf in a human lifetime, and to see those distant icy moons not as subjects of a once-in-a-generation flyby, but as regular ports of call in an expansive interplanetary future. The promise of advanced propulsion offers a future where the time barrier might crumble, yet it immediately highlights a fundamental schism in how we explore. Even if we develop engines that can get a spacecraft to Jupiter in 6 months, the missions we send will fall into two utterly distinct categories with opposite relationships to time: the robotic and the human. These are not just different scales of the same endeavour, they are different philosophies of exploration, with timelines and tolerances that guarantee Jupiter will remain a robotic frontier for generations to come. Robotic missions, like Juno or the upcoming Europa Clipper, are engineered with a scientist's patience. Their very design embraces the long cruise. Their electronics can be powered down into a hibernation state for years, awakened periodically for checkups and course corrections. They do not get bored, they do not get lonely, and they do not suffer from muscle atrophy. For a robot, time is a resource to be spent, often in exchange for mass and cost savings. This allows mission planners to choose the most economical trajectory, the one that requires the least fuel, even if it takes 5 or 6 years. The scientific payload, carefully selected over a decade of debate, is built for the long haul. Its instruments are designed to wait, to remain calibrated in the cold and dark, and then to spring to life for a few precious hours or years of intense activity at the destination. The science goals themselves are tailored to this reality. We ask questions that can be answered by a patient observer. We plan orbital tours that unfold over months, mapping gravity fields, observing atmospheric changes over time, and building up a statistical picture of a dynamic system. The long cruise is even utilised. It is a time for instrument calibration, for cosmic background measurements, and for testing systems in the deep space environment. The entire enterprise is optimised for cost, scientific return, and reliability over a multi-year timeline. The duration is not a flaw, it is a feature of the design philosophy. A human mission, in stark contrast, would treat time as the primary enemy to be defeated. Every day in transit is a day of risk, a day of radiation exposure, a day of consumable depletion, and a day of physiological and psychological strain. The mission architecture would be turned inside out. Instead of optimizing for lowest fuel cost, you would optimize for shortest transit time, regardless of the propulsion cost. The spacecraft would no longer be a minimalistic science platform, it would be a life-supporting fortress. Its mass would be dominated not by instruments, but by shielding, habitats, food, water, air recyclers, exercise equipment, and redundant systems to protect fragile human biology. The science goals for a human mission would be different too. While humans bring unparalleled flexibility and reasoning to exploration, their presence is not about conducting long-term passive observations. It is about rapid assessment, complex decision-making, and hands-on activities that are impossible for robots, like intricate repairs or selecting samples with geological intuition. But to justify the immense cost and risk, you would likely not send humans just to orbit Jupiter. You would send them to land on a moon like Callisto, or to establish a presence. This adds yet more layers of complexity and mass for landers, surface habitats, and ascent vehicles. The propulsion system needed to push this colossal mass on a fast trajectory is why concepts like nuclear thermal or nuclear electric propulsion are not just nice to have for human exploration, they're absolute prerequisites. The timeline for a human mission is therefore compressed by necessity. You're not looking at a 5-year cruise, you're looking at a 2-year maximum, preferably less, transit to minimise the hazards. This demands a completely different infrastructure, a different launch vehicle capability, and a different level of financial and political commitment. The development path for such a mission is measured in decades, and budgets comparable to the Apollo program, but sustained over a much longer period. Given these diametrically opposed paradigms, the practical reality is clear. Robotic missions will continue to be the workhorses of Jovian exploration for the foreseeable future, likely for the rest of this century. They're affordable, politically sustainable, and scientifically magnificent. They can take the slow road, and in doing so, they deliver phenomenal value. A mission like Europa Clipper, costing a few $1 billion and taking 5.5 years to get there, is a manageable project that will revolutionize our understanding of an ocean world. A human mission to achieve the same thing would cost hundreds of billions, take 30 years to develop, and put lives at immense risk. The risk-to-reward calculation for now firmly favours the robots. This is not to say human exploration lacks value, it is the ultimate expression of our curiosity. But it follows a different track, one that is logically and technologically sequential. We will go back to the moon to learn how to live on another world. We will go to Mars to learn how to survive a long-duration mission relatively close to home. Each step builds the technology and the operational experience for the next. Jupiter is not the next step after Mars, it is several steps beyond. The robotic path and the human path are, for the time being, parallel but separate lines. The robots sprint ahead, scouting the territory, answering the foundational science questions, and identifying the most interesting places. The human technology, lumbering and slow to develop, follows far behind. One day perhaps the lines may converge. If we master fusion propulsion or another breakthrough technology that makes a one-year journey to Jupiter with a massive spacecraft routine, then the calculus changes. But even then, the first human missions will likely be to destinations where we can achieve something uniquely human, like establishing a research base on Callisto, rather than simply repeating what robots did 50 years prior. Until that distant convergence, the travel times to Jupiter will tell two different stories. For our robotic avatars, the time is a testament to clever engineering and scientific patience, a long arc that yields decades of discovery. For our human aspirations, that same time is a formidable wall, reminding us of our biological fragility and pushing us to invent a new way to travel. So, when we look at the timeline of missions past and future, we are seeing the story of two different explorers. One is made of silicon and steel, and for it time is a tool. The other is made of flesh and blood, and for it time is a trial. Jupiter waits for both, but for a long while yet, it will only know the quiet, patient touch of our machines. That clear divide between robotic patience and human urgency brings us to a subtle but crucial point about those long robotic cruises. We often frame the travel time as a simple waiting period, an empty stretch between the excitement of launch and the thrill of arrival. But in reality, for the mission teams and for the spacecraft itself, the cruise is anything but empty. It is a vital, active phase of the mission, a period of preparation, calibration, and even bonus science that transforms the journey from a passive coast into an integral part of the exploration process. Think of it not as a void, but as a long, quiet runway where everything is made ready for the main event. From an engineering standpoint, the cruise is a gift. It is a prolonged shakedown period in the actual environment of deep space. After the violent vibrations of launch and the stressful deployment of solar panels and antennas, the spacecraft enters the relative calm of its interplanetary trajectory. This is when engineers can carefully turn on each instrument one by one and run a series of checkouts. They can test the cameras by taking pictures of stars or distant galaxies, which serve as perfect calibration targets. They can exercise the moving parts, the scan platforms, the antenna gimbals, the filter wheels on spectrometers. They can monitor the power system's performance as the spacecraft gets farther from the sun and track the thermal balance as it experiences the growing cold. Any quirks or minor issues discovered during this period can be diagnosed and often corrected with software updates or revised operational procedures. Discovering a problem a year into the cruise is far better than discovering it during the high-stakes Jupiter orbit insertion burn. This extended testing builds immense confidence. By the time the spacecraft reaches Jupiter, the team on Earth knows its machine intimately. They know how its instruments behave, how its systems respond to commands, and what its limitations are. This familiarity is priceless when every decision at Jupiter must be perfect and pre-programmed. The cruise also allows for crucial trajectory refinement. The initial launch and departure burn are never perfectly exact. Over the months, navigators use the Deep Space Network to track the spacecraft's position with incredible precision by measuring the Doppler shift and time delay of its radio signal. They can then calculate tiny mid-course correction maneuvers. These are small engine burns, sometimes just a few seconds long, that nudge the trajectory back onto the perfect path. The long cruise provides the time to measure, calculate, and execute these corrections with leisure and precision, ensuring the spacecraft hits its celestial keyhole at Jupiter. For missions using gravity assists, the cruise phase includes these planetary encounters, which are major events in themselves. The flyby of Earth or Venus is not just a passive slingshot, it is a full dress rehearsal for the kind of fast-paced precision navigation that will be required at Jupiter. The spacecraft practices taking optical navigation images of the planet against the star field to determine its position autonomously. The science instruments get a chance to operate during a planetary encounter, collecting valuable data and proving their functionality. The Galileo mission's flybys of Venus and Earth were not just for gravity, they were essential tests of its cameras and other instruments, which had been delayed in deployment due to a stuck antenna. Without that long cruise and those rehearsals, the mission would have been far less prepared for Jupiter. Then there is the pure science that can be done en route. This is often called cruise science, and it turns the transit from a cost into an opportunity. The spacecraft's instruments can be used to observe things that are difficult to study from Earth. For example, a spacecraft heading to Jupiter is on a unique path through the solar system. It can measure the solar wind, a stream of charged particles from the Sun, in regions far from Earth. It can look back and take calibrated images of the Earth and Moon together, providing perspective and testing camera settings. It can observe asteroids it passes near, or study cosmic dust distribution. The New Horizons mission, during its long cruise to Pluto, made observations of Jupiter's magnetosphere, studied the plasma environment in the outer solar system, and even looked at distant Kuiper Belt objects. The Juno spacecraft, on its way to Jupiter, was reactivated during its Earth flyby to calibrate its instruments and take some stunning images of the Earth-Moon system. This science is not the primary goal, but it is a valuable bonus that adds to our understanding of the interplanetary environment and keeps the science teams engaged and practiced. From a public engagement and programmatic perspective, the long cruise also serves a purpose. It allows for a gradual build-up of awareness and anticipation. Mission teams can release early calibration images, talk about the engineering checks, and explain the science of the gravity assists. This keeps the mission in the public eye, albeit quietly, and helps build toward the crescendo of arrival. For a mission that takes 5 years to get there, if the public only heard about it at launch, and then again 5 years later, interest would fade. The cruise phase provides a narrative thread, a series of milestones, first images from space, successful Earth flyby, instrument checkouts that maintain a connection. Finally, for the scientists and engineers, the cruise is a psychological and practical bridge. It is a time to finalise the incredibly detailed operational plans for the primary mission. Planning the orbital tour of Jupiter's moons, or the sequence of observations during orbit insertion, is a monumental task. The cruise period gives the teams the time to run simulations, debate priorities, and write and test the thousands of commands that will guide the spacecraft during its prime mission. It is a period of intense focused preparation, where the lessons from the early checkouts are incorporated into the final plans. So while the clock is ticking and everyone is eager for the main science to begin, the cruise is not wasted time. It is the essential process of becoming a deep space explorer. The spacecraft sheds its identity as a cargo in a rocket fairing and becomes a functioning observatory. The team transitions from the hectic pace of launch operations to the meticulous, long-range rhythm of interplanetary flight. The journey itself becomes a teacher, revealing the spacecraft's personality and preparing both machine and humans for the moment of truth. In a way, the necessity of the long cruise enforces a discipline and a thoroughness that might otherwise be rushed. It forces a slow, methodical approach that results in more robust and successful missions. We learn to integrate the journey into the science, to use every moment productively. This mindset is perhaps the defining characteristic of deep space exploration in the robotic age. We're not just destination-driven, we are journey-aware. We pack our spacecraft not just for the final destination, but for the long road itself, ensuring that even the quiet years between worlds contribute to the grand goal of understanding our place in the solar system. The travel time to Jupiter, therefore, is not an empty interval on a timeline. It is a rich, multi-layered phase of the mission where engineering is validated, navigation is perfected, bonus science is captured, and the final act is meticulously rehearsed. It is the deep breath before the plunge, and it is every bit as critical as the splash. Building on that idea of the cruise as a productive and necessary weight, we are forced to confront a broader, more ingrained reality of deep space travel. All these factors, the patient cruise, the years-long trajectories, the multi-decade mission life cycles, point to a fundamental truth that transcends engineering. The ultimate frontier in exploring our solar system is not just distance or radiation or propulsion. It is time itself. These immense travel durations impose a rhythm of discovery that is utterly alien to our modern experience. A rhythm measured in years and careers rather than in minutes and news cycles. This shift in tempo is perhaps the most profound cultural and organisational challenge of interplanetary exploration. We live in a world of instant communication, next-day delivery, and rapidly shifting trends. Our institutions often operate on quarterly reports or electoral cycles, but a mission to Jupiter laughs at these timescales. From initial concept to final data analysis, such a mission can easily span 20 or 30 years. The scientists who conceive the mission might be in their 30s. By the time the spacecraft reaches its destination, they could be in their 50s. The young engineers who build it might lead the operations team a decade later. This is a generational enterprise. It requires a form of long-term thinking and commitment that is rare in human affairs. It demands that funding agencies and governments maintain support across political changes and economic shifts. It asks the public to stay interested in a project that launched when a teenager was born and delivers its headline results when that teenager might have children of their own. This timescale is not an accident. It is a direct consequence of the physics we have discussed. The distances are so vast that, even at the speeds we can achieve, travel takes years. The light speed delay means communication is not a conversation but a slow exchange of letters. This slowness is baked into the cosmos. Accepting these timescales is, in a very real sense, accepting our true place in the universe. We are not the centre of a small, quick neighbourhood. We are inhabitants of a vast and mostly empty stage, where the speed of light is a limiting constant and planetary orbits are the slow hands of a giant clock. When we launch a spacecraft like Voyager or New Horizons, we are sending a message not just into space, but into the future. We are committing our knowledge and our questions to a vessel that will deliver them to a point in time years downstream. This long-term perspective has practical effects on how missions are run. It fosters a culture of extreme care and planning. There is no move fast and break things in deep space. A mistake in a command sequence, if not caught, might only manifest 6 years later when the spacecraft fails to enter orbit, with no possibility of a recall or fix. This forces a discipline, a thoroughness, and a culture of testing that is perhaps unique. It also creates a beautiful human chain of knowledge. Veteran engineers pass down hard-won lessons about radiation effects or trajectory design to younger team members who will be the ones operating the spacecraft at Jupiter. The mission becomes a living entity that outlives any single person's daily involvement. For the public, this elongated timeline can be challenging. We are used to the drama of a launch, then the quick payoff of a landing or a rendezvous. With Jupiter missions, the launch is just the first note of a very long symphony. The melody does not pick up again for years. This requires a different kind of storytelling, one that finds value in the quiet periods, the successful engine test a year into cruise, the beautiful image of Earth from 1,000,000 miles away, the precise gravity assist at Venus. These are the chapters that keep the story alive. The payoff is worth it, but it is deferred in a way that tests our collective attention span. Yet this very deferral is what makes the final moment so powerful. When Juno finally sent back its first images of Jupiter's poles, it was the culmination of a 5-year journey and a decade of work before that. The emotional weight of that data was magnified by the wait. In a world of instant updates, there is something deeply satisfying about an achievement that simply could not be rushed. It reminds us that some things must unfold at their own pace, dictated by the laws of nature. This relationship with time also defines our current technological plateau. The 5-year journey is a signature of our era, a measure of what is possible with chemical rockets and gravity assists. It is not a permanent condition. As we have discussed, the drive to shorten this time is a powerful engine for innovation. The development of nuclear thermal propulsion, or eventually fusion, is fundamentally a war against time. It is an attempt to align the timescale of human exploration with the timescale of human biology and psychology. We want to shrink the solar system not in absolute distance, but in travel time, to make it comprehensible and accessible to a civilization that lives for about 80 years. So, the question of how long does it take to get to Jupiter is, in the end, a mirror. It reflects our current technological capabilities, our willingness to plan for the long term, and our patience as a species. It measures the gap between our curiosity and our reach. For now, that gap is measured in years, and we bridge it with brilliant engineering, meticulous planning, and robotic proxies. But the relentless effort to reduce that number, to turn years into months, is a sign of our ambition to not just send probes, but to eventually extend our presence. The time it takes is more than a number. It is a statement. A 5-year journey says we're willing to wait, to invest in a future we may not immediately see, for knowledge that will redefine in our textbooks. A future 1-year journey would say we are mastering our environment, bending physics to our will, and stepping closer to becoming a multi-planet species. Both statements are true at different points in our history. Right now we are in the era of the long journey, the patient probe, the generational project, and there is a profound dignity in that. It teaches us humility before the scale of the cosmos, and it celebrates the human qualities of perseverance and long-term thinking. Every mission that departs for Jupiter is a bet on the future, a testament to our belief that the people who come after us will still care about the data, will still be eager for discovery, and will still look up at that bright dot in the sky with wonder. It connects generations through a shared quest. So, when you see the latest stunning image from the Jovian system, remember the timeline. Remember that the light in that image left Jupiter months ago. Remember that the spacecraft that took it left Earth years ago. Remember that the people who designed it started their work decades ago. That image is a message from the past, a gift to the present, and an inspiration for the future. It is a product of time used well, time endured, and time ultimately conquered by our persistent desire to know what lies beyond the next horizon. The journey to Jupiter, in all its duration, is not just a trip through space. It is a voyage through time, and every spacecraft is a time ship, carrying our hopes from one era to the next, proving that even against the vast clockwork of the solar system, human curiosity can keep pace.